so I'm just going to kickstart the morning and then we'll go from there. So, good morning, good afternoon, or good evening, everyone. Thank you for joining the NSIRC Research and Innovation Conference from wherever you are in the world right now. As you can see on the screen, we've had some excellent sponsors this year, so I'd just like to express my gratitude to you all on behalf of NSIRC. We couldn't be where we are without you, so thank you for your support. And just before I move on to the conference itself, as part of the aim to improve TWI's safety culture, I'd just like to promote this month's Health and Safety Moment. So as we continue to work from home and are spending longer staring at our screens, it's vitally important to ensure you have good lighting when you're in front of the computer, as you could see the health of your eyes deteriorating over time. As a lot of us will be working in our living rooms, at the kitchen table, or squeezed into our bedrooms, you should try and keep your space as clear as you can, as it will help your mental health throughout the day. Clear space is a clear mind. And lastly, this is unlikely in your home, but if you are rushing around or trying to get to the door quickly, do not run down the stairs. You are likely to trip and fall. And if no one else is at home, you could be laying down on the floor in some pain for quite some time on your own. No delivery is worth hurting yourself for. I have said the delivery driver will wait, but as we all know, they don't tend to hang around for long. So for those of us who joined us last year for NSIRC 2020 live conference, you may be familiar with the setup and running of the day. But for those who are new for this year, I'll explain what the day will consist of in a little bit more detail. So across the 2 days, we'll hear from over 35 NSIRC PhD students, as well as a selection of our project leaders who are working on TWI's core research program, or CRP. Each day will be split into 2 parallel sessions, and all delegates will have the option to join session A or session B. Throughout both days, you'll have the opportunity to move between both rooms at your own leisure. Once we've heard from our keynote speaker this morning, we will send a link in the chat box for those who wish to join session B. And for those who would like to stay in session A, you'll just stay where you are, and I'll explain that a little bit further later on. So for this year's conference, we're lucky enough to be joined by 2 exceptional keynote speakers, and I look forward to hearing them both. So this morning, we'll hear from Luca Corradi, and tomorrow we'll hear from Professor Mark Thompson. Our first year NSIRC PhD students have produced some posters based on the research they've achieved so far in their course, and to explain what their plans are for the research in their future. These posters can be found on our website on the conference page. So the link is on the screen, and also you should be able to find it from your emails that we've previously sent out leading up to the conference. So please do take a look. Feel free to email the author if you would like to discuss further, to discuss their research topics. And finally, if you have any difficulties throughout the day, please do send us an email. The team are available. Please do contact us via inquiries@nsirc.co.uk, and someone will get back to you as soon as they can. Someone is monitoring this throughout both today and tomorrow. So if you are having any connection issues or not sure what link to use to join each session, please do let us know, and we'll be there to help you out. So without any further ado, I'll pass over to Tat-Hean Gan's presentation, who's the director of NSIRC, to introduce NSIRC and the core research program. Thank you.
Good morning, ladies and gentlemen. Welcome to the NSIRC 2021 conference. I'm delighted to see so many of you here today to join us at our conference. I'm here to talk about NSIRC and also our core research program at TWI. My name is Tat-Hean Gan. I'm the director of NSIRC. So what is NSIRC? NSIRC stands for the National Structural Integrity Research Center. It was established in 2012 with a funding of £150 million over 10 years. It is a unique collaboration between our academic partners and also TWI industrial members. We have 3 founder sponsors who are Lloyd's Register Foundation, TWI, and BP. At the same time, the government has also co-funded the program. The funding comes from the Regional Growth Fund and that goes to Brunel University London. With this funding, we have world-class purpose-built facilities and equipment for structural integrity research that can be utilized by our university partners and also industry members. So what's our vision and mission? Our vision is to become a world-renowned center of industry-driven academic excellence in the field of structural integrity. The mission being, create a critical mass of research informed by industrial needs, develop postgraduate programs, and train the next generation researchers and engineers. We would also like to become a research provider of choice for industry in the area of structural integrity. We would like to contribute and develop effective standards and regulations. And finally, we would like to translate our development from science into industrial applications. Hopefully, we can develop products and services at the end of the program. So the above diagram shows you there's a gap between industry and academia. There are many reasons for that. For example, you can see here, there are different types of mindsets between the academia and industries, lack of exposures between academia and the industries. In terms of pursuing different goals, again, you can see there's a gap between those two sectors. The solutions that are provided by the researchers sometimes is not ready for commercialization, and the risks are very high. So with that, it is our duty as NSIRC to bridge the gap. I would like to say that we have successfully do this, as you can see in the presentation later. The diagram above shows you how we have developed an industrial pool research programs. So you can see that there are strong demands in the end user sector, looking for emerging technologies that can be utilized by the industry. How do we do this? So as TWI, we work with our industrial members to identify the latest technology, and this is channeled through the core research program. From that, we then work with our NSIRC sponsors, again, who are TWI, Lloyd's Register Foundation, MPP. Together, we formed an industrial needs. By identifying the challenges, we then cascade it to our industrial partners and also to universities, and this forms PhD programs. As you can see from this diagram, NSIRC sits nicely within the circle where we get to learn about all industrial challenges, and this can be taken forward by our university partners. So let's look at the NSIRC program. So currently we have 3 types of programs. Firstly, it's a doctorate program. So our flagship program is PhD in Structural Integrity, where we work with 45 UK, European, and international universities to deliver the program. The students, although they're registered in different universities, they sit in TWI and work alongside with our engineers. Recently, we established a new program with Anglia Ruskin University called the PhD in Innovation Management. The second program is Masters in Engineering, where we currently now have 5 master's programs in the field of engineering, as you can see from the 5 boxes at the bottom. So this varies from AI programs to asset management, oil and gas, and lightweight structure of impact engineering. These programs are run by University of Essex and Brunel University London. We have a third program, which is the Masters in Management. So in this case, we have MBA run by De Montfort University and Masters in Engineering, Leadership and Management by Aston University. So these programs are co-developed with TWI and its industrial members. Some highlights for NSIRC. To date, there are 327 students enrolled, of which 179 are doctorate and 148 are masters. We are proud to say that 31% of our students are female. whereas if you look at the UK engineering uptake, it's only 11%. We have 100% employment within 1 year of graduation. So this is the strength of NSIRC in the sense. We have contributed to 39 codes and standards to date, 15 awards for research excellence, and we have published 279 journal and conference publications. So these are very well achieved by our students and our staff members jointly work together. We have also done 350 days of community outreach activities. So these are the activities that we have been to schools and colleges to promote STEM subjects so that we can encourage more uptake in the field of engineering. Let's look at some of the impact that has been created by NSIRC. So I mentioned about the pillars that we have in our vision and mission. So here is to show you a few proof that we have done. The slide above shows you some of the achievement by our students who have published in well-known journals and also special editions, plus conferences. For example, Women in Sensors Journal, and also some of them have contributed to the NAFEM World Congress, plus also taken part in the additive manufacturing publication. So these are the key subjects that we have done to date. We have done 840 person years of industrial research by our students in many areas. So these are highlighted in the honeycomb. As you can see, subject varies from fitness for service, structural health monitoring, condition monitoring, robotics and automation, additive manufacturing, and many more. If you wish to find out more, please visit our website. We have also trained the next generation engineers and researchers. As an example, you can see Rosa here. During her study with us, she has been to Spain to carry out her research placement. So she has been to MCTS to carry out her test in terms of long-term corrosion performance of coatings. And eventually, she was also recruited by them. It shows that industrial placement is very important. Next is on codes and development of standards. So in this case, 39 PhDs have contributed to existing codes and standards since 2012. So many effort has been put together to make this happen. Our research are sponsored by Lloyd's Register Foundation and also TWA Core Research Program. With that, we also have contributed to 2 new standards, and these are on machine learning for ultrasonic inspection and also additive manufacturing metallic parts. So we're actively engaging in membership committees so that we can help to influence the committee as we go along, as our research will enhance the standards. We are also the research provider of choice by many companies nowadays. So here I've selected in the oil and gas sector, we set up the non-metallic innovation centers funded by Saudi Aramco or Aramco Tech, ADNOC and TWI, with the aim to develop the next generation polymer pipes for oil and gas application. In this case, our student Hamad, funded by ADNOC, has taken forward our NSIRC program with the University of Cambridge to look into the method for assessing polymer pipes and also looking at the NDT methods of assessing them. The aim of this program is to see how we can eventually commercialize the output, the outcome of the research. We have also translated our development from science into products and services. In this case, we have brought up the TRLs from fundamental research, where it started with NSIRC PhDs, and it is now being commercialized by TWI. So it is a PhD program completed by David Williams on the use of Cole's isomeric plasma treatment for the structural adhesive bonding of metals. So the program was funded by TWCRP, and it has been successfully translated into a single client project in the renewable sector. Looking into the future, we hope to expand more industry uptake of our NSIRC program. So we already have expanded the program initially with 3 industrial sponsors. So we have TWI, Lloyd's Register Foundation, and AP. We now have Saudi Aramco, ADNOC, and recently also BAE Systems. We are looking at accrediting our NSIRC PhDs. So currently we're in discussion to see how we can establish this for our future PhD students. We are working towards internationalizing our NSIRC program. So we are currently in discussion with various countries to see how we can expand NSIRC, and the discussion recently has been very positive. Hopefully this will be taken forward next year. We are also looking for more leveraging for sponsors in order to maximize or create more values for them, which means that we get to attract more students, also to fund them. At the same time, we can expand our programs, not only in Cambridge, but also worldwide. And finally, we would like to commercialize the output from our research. So this has been part of our mission throughout these times. We are also uniting all our research programs. So here we have the research and innovation ecosystem. We get to learn from the industry. So on the fundamental side, NSIRC and core research program will develop the research, understand how things can be achieved, understanding the concept, proof of concept. We then further enhance it and offering the outcome or the solutions to our members through single client or joint industrial programs. Collaborative projects allow us to further enhance our research. So usually it sits in the middle of TRL. By doing that, we close the loop of the ecosystem by understanding the industry needs developed through TWI and NSIRC with its members to address the R&D required in the market. So what is core research program of TWI? So here, the program is funded by TWI industry members in order to develop early stage technologies that can be utilized by our members. It is broad, it is cross sectors, and the aim is to carry out fundamental research. So in this case, if it's PhD, it will be done by NSIRC, and then hopefully with the output, it can be technology transferred into joint industry project or single client projects. It enables us as in TWI and also our members to create competitive advantage by learning new ideas or concept and then translate them into new knowledge that can be utilized in the manufacturing plant or for services. We recently have developed a new roadmap with our core research program members. So here we have established 4 themes. The first theme is on AI and data science. Second is on smart manufacturing. Third is on new materials and circular economy. So this is linked to, for example, polymers, advanced coatings. And the fourth area is on net zero, which we focus a lot on hydrogen and low carbon economy. These 4 areas will work across 4 technical teams, for example, joining, fabrication, inspection and monitoring, structural integrity, and materials. At the same time, we're keen to push for new codes and standards through our programs. We will now link all our NSIRC research with our CRP roadmap from now on. I would like to end my presentation with an example of a case study from our CRP. So you can see that it is very challenging, and there's a strong need by our members. So this project is on hydrogen enrichment of high-strength precipitation, hardenable nickel alloys. As you can see in the structure in the photograph, it's very complex, where you have 3 layers of structures. So here, our research look into different types of stress concentration and also microstructure. So by understanding the structure, we get to develop a better stress-resistant material in this case. So these are very much addressing the response or the need of our members. So hopefully we will do that with NSIRC at the same time as well from now on. With this, I would like to leave you with our NSIRC conference. I hope you will enjoy the 2 days. And if there's any questions, please contact our staff member or please visit our website. Thank you very much.
Excellent. I'd just like to thank Tat-Hean for his presentation there. I hope you all managed to learn a little bit more about what we do at NSIRC and in the core research programme. And if anyone has any questions regarding NSIRC or CRP, please do send us an email via inquiries@nsirc.co.uk and we'll point you in the right direction. Now, I'm very pleased to introduce our first keynote speaker of the conference for 2021, Luca Corradi, who is the Innovation Network Director at the Net Zero Technology Centre. Luca will be giving his presentation of Scanning the Horizon for a Net Zero Future. Thank you for joining us today, Luca, and I'll pass over to you.
Thank you for having me, Chloe, and it's a pleasure to speak to this audience. And actually, it's a lovely segue from the end of the previous presentation. We were talking about the Net Zero Roadmap. So, Net Zero Roadmap is part of what we do. And so today, I'd like to give you an overview of an introduction to the Net Zero Technology Center, given we are talking about Net Zero, and about me and what I do, and why scanning the horizon, I think, is a very important activity, especially these days. And so we'll talk a bit about what is on the horizon for a net zero perspective, and take a deep dive, forgive the pun, in the North Sea or the UK continental shelf, and what does it mean for the oil and gas industry in the UK. And talk about, how do we do this horizon scanning? Because that's also something that I think might be very interesting for researchers, PhD students, and all of our audience as well. So that's pretty much the agenda. So let me share my screen and use a couple of slides. Screen number 2 and share. And if you give me a nod that you see it, fantastic. Very good. So a couple of words about the Net Zero Technology Center, right? So our mission is to develop and deploy technology to accelerate the oil and gas industry transition to an affordable net zero future. And so that's what we do. And we were set up as a non-profit organization. We are a non-profit organization co-funded by the governments, UK and Scottish government, and industry. And since the inception in 2017, as part of the Aberdeen City Region deal, we have been champions of the energy transition. So we were created to support the oil and gas industry to make it more efficient. But the horizon scanning activity started there, and the horizon scanning activity is about what's lay ahead in the future and what does it mean for us, for the industry. And so this is what, a couple of numbers there that we've seen previously for NSIRC as well. So everybody has a slide with numbers. But we've invested about 176 million, co-invested with industry in new technologies, screening 1,300 technologies and in 280 projects, including many field trials to see if it works, and to push them for adoption. So this is a bit our numbers, and I'll be happy to discuss and answer any questions, but move on and try to get to the core, which is not this, but this is just an introduction, a quick introduction about me and where I come from. So I got that fancy title of the Innovation Network Director, and even the fancier activity of doing the horizon scanning for the Net Zero Technology Center. And I came to this after a career as a management consultant after graduation in economics with a specialization in change management. And that change management, that focus on technology and how that changed the life and the work. And I would dare to say a curious mind, took me around the world with Accenture, where I worked for more than 21 years, around the world, literally working for the energy industry in many countries, and understanding how energy is actually very important, how critical energy is. Everybody has got their own field, but energy to me is absolutely central. But energy has a challenge, right? And the challenge is very, very relevant and very, very real and more visible in the past few years. So move on. I don't know if you've seen this before. I love this representation. This is called the warming stripes. And each bar represents 1 year from 1850 to today. And the color resembles the French flag in a way. And I like the link to the Paris Agreement of 2015. But the color represents how colder or warmer than the average that year has been. And you can see that the past 40 years have been very hot, and they're getting hotter. The red is getting darker. So this is another way of looking at the same information. So this is what's happening. This is how temperatures are increasing. And all of this, I'm sure, because you live in the real world, and this is not new. But I think it's sometimes good to put some fact and some graph. And you may think that the difference of 1 degree doesn't really make a big difference, but it does. And I don't have to teach to an audience of scientists about that. But the impact and the increase in frequency and of more hot weather or extreme hot weather is coming and is already happening. And Madagascar is going these days through a terrible drought that is. Of course, it's difficult to relate everything specific to climate change, but it's obvious if you want to. But that challenge of net zero, and therefore the challenge which is led by the consumption of fossil fuels, has to match another challenge, which is also looking at horizon and looking at the whole world, and not looking at our small segment of the planet. And it's useful to remind ourselves of this is a global population of about 8 billion people. Each of these little figure represent 1 billion people. And the orange dots are the amount of CO2 equivalent by person in those 4 levels of income. And that's the reality of the world, right? So we tend to think on the level 4, and I bet that many people have a better kitchen than that. But the rest of the world, the 7 billion people are trying to get to that level. Now, the challenge is how do we help those people get to that level, and that require energy? How do we help them get into that level of lifestyle without getting to that level of emissions, and at the same time reduce those emissions per capita? So this is the big challenge of today and tomorrow. And that is difficult, because this is where we're going. The current policies are taking to 2.7, 3.1, and the pledges and targets of the Paris Agreement are taking to 2.4 degrees Celsius increase, and the optimistic one to 2. So to get to the 1.5 is very, very difficult, and a lot needs to be done. And 1.5 is very important. Again, you might think 1.5, 2 degrees, what's the difference? Well, first of all, it's very difficult that we can achieve the 2, but this graph, from the IPCC report is showing the impact of the increase in temperature on the risk for various components or ecosystem or components of the planet, but the planet related to human activity, tourism, crop yields, but flooding, coastal flooding, terrestrial ecosystem, the Arctic region, mangroves and corals, and you can see that the corals are gone, or they're definitely on their way to go. But those 2 lines, the 2 degrees and the 1.5, shows that a lot of the very, very high risk can be brought down to high and moderate. Not great news, but better than very high. So it is difficult. And it is difficult because of what is called there was a graph there that disappeared, but what is called the carbon budget. How much can we still produce and emit? And this is slide from the Climate Action Tracker, updated in July. It shows how we're doing. This is, in the Climate Action Tracker website, you can find different maps based on technology deployment, policy, and a number of other things. So this is sort of a summary view. that basically show that nobody's doing a great job. And most of us are in the insufficient activity, with some highly insufficient, some critical insufficient, no role model, and only Morocco seems to be compatible with the Paris Agreement, having implemented two big solar power plants, and having probably not less demand for power and energy than other places. But that's not enough. And so, looking at the technology coming from the Net Zero Technology Center, this is another summary from the International Energy Agency, which is looking at tracking the technology progress, in buildings, in power, in integration, in transport, in fuel supply. And you can see a lot of red and yellow dots there, showing that we're not on track or not there yet. From iron and steel production and cement, which is by the production process emitting a lot, but a lot of stuff. We don't have the time to go into the detail, but the technology, when you hear we have the technology, well, yeah, we have the technology to do something, but there's a lot of innovation and a lot of deployment at scale that is still required to make that technology and that transition affordable. So that's why an acceleration is needed. But let's have a look at in the real world, right? So what's going on in the various sectors that are more responsible for those emissions. So power, and taking a UK view here only, power is clearly going towards renewables. There's been a massive reduction in the emissions associated with the power generation in the UK. A lot of that is wind. Offshore wind is developing big time, including floating offshore wind. And the target, as you can see from the CCC there, is to go to something between 65 to 125 gigawatt by 2050. And the gap there is driven by how much of that is needed to produce green hydrogen. So the intermediate is 40 gigawatt, which is 4 times what we have now, and 65 to 125 is 10 times what we have now. So that's a big effort in deployment, which raises a number of questions and challenges, of course, but that seems to be the direction. So renewables for power, but then the renewables bring the question of energy conservation or energy storage, because the wind doesn't blow in the place where you need it. A lot of the wind is in north of Scotland, and a lot of the demand for electricity is down in the south around London, and also the seasonality and the variability. So that's a complex system, but clearly going towards renewables and a massive reduction in the consumption of oil and gas as recommended by the Committee on Climate Change in the 6th carbon budget in this scenario. Manufacturing is also another responsible for a lot of emissions. If you look at cement, 8% of global emission, and steel 5% and 4% in all the petrochemical sector. So this is where fuel replacement and hydrogen that I mentioned before is going to probably play a big role, and carbon capture, sequestration, and storage. You can see on the top of the 5, I can count the 6 key industrial clusters in the UK, where most of the industrial emissions are concentrated, and that is the Industrial Decarbonisation Challenge Fund and Industrial Decarbonisation Program by the UK government. And BEIS is aiming at achieving at least 2 of those to start being net zero by 2030, and then decarbonizing the industrial sector. Again, there's a lot of innovation required, a lot of technology to improve what the current technology is to make that happen. And so each of these clusters now going through a road mapping on how to make that happen. We are part of a couple of them. And then transport, domestic heat construction. So we probably don't have the time to go too much in detail here, but showing that hydrogen or electric vehicles, I would stay away from the either or. It's going to be an and, especially for different uses. When you look at heavy good vehicles or return to fleet, sometimes hydrogen makes more sense, but electric vehicles are obviously more efficient. The distribution and the infrastructure for refueling and is another challenge. Marine, a lot of work being done in ammonia or biofuels, but hydrogen as well. You can see hydrogen coming all over the place because of its flexibility, but again, it's not the panacea. It's one of the solution. And construction, of course, low carbon cement and carbon negative material, and design for the user. Make a comment here because I think focus on NSIRC is structural integrity, and I think maybe there is, but our recommendation is, okay, let's look at not only the integrity while the building is there, while the infrastructure is there, but how can we make those infrastructure designed to be easily decommissioned, disassembled, recycled, reused, as opposed to the classic linear circle of install, maintain, and then dismiss. So that, I think, is a critical skill to develop. I'll say, what does it mean for the North Sea? Well, it is an opportunity, because clearly, the oil and gas industry will go down. I will stress the point that it's not a switch, an overnight switch, because at the moment the UK is importing a lot of its energy requirement, a lot of its oil and gas. So we produce in the UK less than half of the consumption of oil and gas. And even the projection of production that would go down just by exhaustion of the field will go down faster than how the demand is predicted to go down or recommended to go down by the Committee on Climate Change. So both import and production domestic will go down, but we will still have a negative deficit. So that means that we need to keep producing some oil because we have a much higher opportunity to control the emissions associated with this production if we do it domestically rather than importing it from elsewhere. So anyway, so that's our vision, if you want, for where the North Sea will be in 2050, and it will be a different North Sea. And it is now basically an oil and gas with a small but growing offshore wind, and two sectors that don't really talk to each other or don't really work together until recently, and we are now working together. But the oil and gas industry in the North Sea in the UK can be a fantastic enabler of that transition if we do it in the right way, because it can have the infrastructure, the ecosystem, the skills, the knowledge, the testing, and the people that can make offshore renewables, including floating wind, hydrogen production, blue and green, and carbon capture and storage for hydrogen, but also for industry, a reality. And I think the key message I would say here, in addition to the fact that it's not a switch, but it will go down on fossil fuel, is that the size of the prize can be bigger than what it is today. Now that requires the development of a local supply chain and local or domestic excellence in innovation and science, which is what you're about. A couple of mentions, you can find these two reports on our website. I'm conscious of time that we develop a vision, because you can scan the horizon and then, okay, this is where it's going, but we want to go in some other direction. So there's this balance between scanning the horizon and trying to influence it. So we developed this vision last year, an integrated energy vision, which showed the potential, show the requirement for investment, but the potential to contribute to the UK economy and the support to jobs in achieving net zero by this much higher integration of different sources, including oil and gas or low carbon, or I'm talking about scope 1 and 2, obviously here, but low carbon oil and gas with hydrogen, carbon capture and storage, and floating wind. Now, I mentioned technology. So is the technology available, ready? Oh, yes, but some of that is there, and that's why we should start deployment projects, producing hydrogen, producing electricity through offshore wind and floating wind, start capture and storage. But it is early stages industry, which with a lack of a big deployment, and that's where you start learning. So we think that the strategy is a kind of a dual strategy. On one side, we need to start deploying projects because we learn by doing, and by scaling up, we have economies of scale. That's the economies coming back from me, and the economy of skills. But at the same time, that can get you to a 30% cost reduction, and we probably need more than that. So we still need, in the meantime, to innovate and to research and to find new way of doing these things. And this page is summarizing some of the highlights from another report, Closing the Gap, that we published last year, which says, okay, what are the key technologies gap where we need to focus our roadmap of technology, innovation, and testing and deploying, because that will make a difference, a significant difference in cost, rather than just deploy and learn from it. So those are the two reports I mentioned that came out of this horizon scanning activity. And I close, talking a little bit about the horizon scanning, the why and how. So why we do it and how we do it. And so the why is should be obvious, right? So it's bringing the outside in, as I call it. It's looking at what's going on across sector, looking at what's going on in society, looking at what is going on in policy and behaviors and thinking, and trying to anticipate and say, okay, what does it mean for it? What is the potential impact, which is the box on the right-hand side? And the potential impact is, needs to be defined in a statement, needs to be defined in a way that can force the attention to what by when. And then is about identifying these trends and assessing the rate of progress and constantly monitoring. And I love this quote by an economist, which is the two classes of forecasters. Those who don't know, and those who don't know, they don't know. So conscious that we don't know, and we try to know by doing this exercise. So in one slide, this is what we do at the NSIRC Technology Center for the horizon scanning. We have a processor, we have a methodology. It's not just a crystal ball. I'm opening the crystal ball. There's circuit and process and method in that. And it starts from selecting the sources, and that is a sample of a number of sources that we monitor. The problem today with all the social media and all the media and all the flow of information is that you might end up listening to the same thing told in different ways many times, and it's still the same source. And you may think that that is a trend, where actually is just an echo of a trend. So variety and the multidisciplinary and also multiple point of view of sources that you scan and look as much as possible to original sources are important. And then we use a weekly cycle, a monthly cycle to discuss and translate those learning into this forecast board, as I call it. And again, is trying to define a sentence. The UK CO2 geological storage will be in place at a larger scale. Yes, no, maybe. And that orange dial is the 2030 gas, and the blue dial is the 2050 gas. And this changes every month when we do this exercise. We have a new question, so we have the standing question, because this is what helps our research, our roadmap, our partner to define, okay, what shall I do? When is the right moment to diversify? When is the right moment to invest? What skills do I need to develop more? And the final bottom left is what we call the high pro matrix. So how much is the progress rate of this technology compared to the hype factor? And the hype factor is how much you hear about in the non-specialized media, and all of a sudden they seem real. Whereas the progress rate is how much money is invested in it and how much research has been done. So it's kind of a follow the money and follow the news, if you want. So that's a quick overview of our horizon scanning and what's in the horizon from a net zero perspective, with a positive note of hello future here. But I think if I had to summarize my key takeaway, on the net zero front, climate change is a complex issue, and it doesn't have one simple solution. And technology, that would be number two, is key and important. And I think the best is coming. It's not yet to come, it's coming. The next year will really determine how much we can innovate, how much we can transform the future by technology innovation, which I think has a key role to play. And the third is that all this can be an opportunity for development of skills, for development of the economy, and that if is depends on how we do it. Again, it's not a simple solution, it's a complex one with unintended consequences. And that's where horizon scanning, I think, is important, because it's difficult, it's hard to plan your future, but having an idea of where this is going and constantly challenging, constantly verifying, it helps, based on evidence, it helps on drawing the roadmap and then trying to develop that roadmap. I will close with a point. I've heard a lot of, I love the presentation was done before me in terms of what your scope is, and as researchers and technology and PhD students, my recommendation is always think about impact. And so that's where horizon scanning can help understanding where the future could be, and you assign probability to it. And then how does that link to the work you're doing? And the work you're doing, what is the impact then on society, on people, on the economy? Because often in my interaction with the university around the UK, I get into lovely technical detail. And I think the best researchers and the most successful one are those that go into that technical detail and love that solution, but have a clear vision of how that solution impacts the future and how we can change it for the better. And I'll stop here, and I hope I didn't go too much beyond time, and we have maybe time for a couple of questions.
Excellent. Thank you very much, Luca. It was a very interesting presentation. I think in this day and age, everyone can relate to what you spoke about today a lot more widely. So thank you for that. Yes, we do have time for a couple of questions. So the first one I will ask is, what do you think are the 3 key barriers to net zero adoption by industry?
I think to net zero reduction, I mean to achieving net zero.
Yes, correct.
Well, in the end, follow the money, right? The economics are the challenge. At the moment, we are not giving the right price to the carbon emission. And therefore, introducing and deploying technology that can reduce the emission from industrial production or going toward net zero is a cost. And the counterfactual, which is the current status quo, burning fossil fuel, doesn't really have the real cost for the planet or for the economy. So that is the concept of externalization in economics that are not included. So, and that is a challenge because although the trading scheme, the European trading scheme, and now the British trading scheme is going towards that direction, is developing a market where you can exchange this credit for emissions until it is an incentive. But finding the right number, the right price is the difficult part, because if it is too high and the profit of the industry are too low, then well, what's the option? I shut down the business here, I shut down the petrochemical plant, and I'll put it back up again in a country that doesn't have that regulation or that price. So that is the second barrier to that, which is it is a global problem and we have local solutions. How do we get that solution to be a global one, a more concerted one? And this will be the fascinating topic, I think, in 8 weeks now in Glasgow, COP26, a big conference on climate change, where all countries are trying to find those type of agreement. Solution might be unilateral solutions. It's been advocated for a carbon border tax. The EU is planning to introduce one in the part of the Green Deal, which means that the goods coming from abroad that don't have a certification of low carbon, will be taxed for that embedded carbon. Everything we have around here is made of petrochemical or is made using petrochemical. And if you want to have a level playing field, you need to make sure that a cement factory or a steel factory in the UK, which produces maybe steel with hydrogen and therefore clean steel, is not disadvantaged by selling that clean steel in the market at a higher price that steel made with coal, in another country. So the challenge there is really one of the challenges that how to make it work, how to consider and then the net zero and the real price of carbon for the planet into the economics of decision making. The second is how to harmonize and coordinate that effort at international level. And I think that the third effort is, I can't not say, is technology and innovation, right? That's the third area where we need to do, because the technology we have today is really can work, but not at the cost that we need it, which would mean drastic impact on the cost of living, on behaviors and etc. that we need to be ready for in a way. Long answer, sorry.
No, absolutely. No, we really appreciate the in-depth answer. I think it helps everyone to understand a little bit more, and everyone can see where the common barriers are and learn from each other as to what the barriers are and where everyone can focus their research on in the future to achieve net zero. So thank you, Luca. We have now run out of time, unfortunately, for your session, Luca. That was really, really interesting. So grateful to have you with us today. So thank you for your presentation and for your preparation time leading up to the event. It's really good to have you with us this morning. And if, unfortunately, we couldn't answer all the questions, but if anyone does have any further questions for Luca, please do send us an email via inquiries@nsirc.co.uk and we'll pass your question on for you. So thank you again for joining us, Luca. Please do stick around to hear some of our PhD student presentations if you have time.
I would love to, unfortunately, but I see this is a recorder, so there might be a chance to look at that later.
It is indeed, yes.
Thank you for having me, and you can contact me on LinkedIn if you want, and if you have further questions that you want to collect, Chloe, I will be happy to answer them offline.
Brilliant, that's really appreciated. Thank you, Luca, and have a good day.
You too, thank you.
Thank you, bye. So thank you, everyone. We'll now be moving on to the rest of the NSIRC Research and Innovation Conference for the day. So we will now be splitting into session A and session B. So if you'd like to stay and listen to the composites and polymer session, please stay where you are. But if you would like to head over to the additive manufacturing session, please click on the link that Daisy has just sent in the chat box now. So that link will just take you from this webinar into another one, and you'll be able to listen to the additive manufacturing session, which is then followed by Industry 4.0. And then we have structural integrity in the afternoon. Throughout the whole day, you are, of course, welcome to come back to session A if you'd like to listen to a particular presentation. So for that, you'll just need to click on the link that you clicked on this morning in your emails to come to this introduction right now. If you are struggling with that throughout the day, Daisy will be able to help you, as well as the team at the inquiries@nsirc.co.uk emails. And of course, as you can see, there's a lot of our NSIRC team here today. So please do send us a chat message and we'll be able to help you switch between wherever you'd like to be. So thank you for joining us, and I hope you all have a fantastic day listening to our PhD and CRP presentations. And with that, I would like to now welcome the composites and polymers session. And for those who'd like to go over to additive manufacturing, please click on the link now and they'll begin their presentations.
Excellent, thank you, Chloe. So again, welcome to the composites and polymer session. Well, this particular session is sponsored by the Brunel Composites Centre, as well as Teesside University. My name is Kevin Hughes, and I'm part of the senior academic team for Brunel University, based here at NSIRC, and I'll be chairing this morning's session. So we've got two presentations before the mid-morning break. So if you do have any questions, please feel free to put them in the Q&A chat box, and we'll either try to answer them live or offline. So without any further ado, I'd like to introduce our first speaker, which is Alessandro Sergi. He's a third-year PhD student with the University of Birmingham, and his presentation will be on the influence of powder characteristics of hot isostatically pressed pure niobium for space applications. So Alessandro, over to you, please.
Yeah, good morning. Thank you. Thank you for the introduction. I'll start now sharing my presentation. Okay. So, good morning, everybody. My name is Alessandro Sergi, and the title of my presentation, I'm an NSIRC PhD student at University of Birmingham, and the title of my presentation is Influence of Powder Characteristics on Hot Isostatically Pressed Pure Niobium for Space Applications. So we'll start with a brief introduction on the requirements for transfer combustion chambers, which is the application we targeted. And then we will explain why we selected pure niobium as a material. Then we'll move on to the experimental procedure where we will describe the experimental plan, and then to the results, including powder characterization, microstructure analysis, and microhardness and tensile properties. And at the end, I will draw some conclusions out of the work. So the application for this study is rocket transfer combustion chambers, and they have very strict applications. The maximum service temperature for this application is above 1450 degrees C, and as we know, not many materials are able to withstand at high temperatures. The components need to withstand high temperature oxidation resistance. This is why normally transfer combustion chambers have an internal high temperature oxidation resistant layer. The yield stress of the material at room temperature should be above 260 megapascal, and components should withstand 1000 thermal cycles in mission operation mode. And lastly, the transfer combustion chamber needs to have a coefficient of thermal expansion similar to titanium 6-4, because the part is joined to another titanium 6-4 component. So now I would like to explain you why we selected pure niobium over the conventionally used alloy, which is C103. So C103 is a niobium alloy composed by 10% hafnium, 1% titanium, and 0.7% of zirconium. We have selected pure niobium because of its high temperature capabilities. In fact, pure niobium is a refractory metals, and among all the refractory metals is the one with the lowest density. It's another important fact is that limited heaping investigation have been performed on this material. This means that we can understand the heap response of pure niobium, and as well, since it's a pure metal, we can try to tailor the microstructure mechanical properties by, for example, changing the process parameters or the powder's characteristics. Then there is the possibility of creating high temperature oxidation resistant coating, which is limited on C103 because of the presence of hafnium, titanium, and zirconium, which can create some authentics, but most importantly, they tend to form brittle intermetallics. There is no generation of prior particle boundaries, the so-called PPBs, during powder or isostatic pressing. That's because niobium has a high solid solubility in oxygen. The high solid solubility of oxygen will tend to put oxygen in solid solution rather than forming oxides on the surface of the powder. And then pure niobium is a low-cost material if compared to C103. So now that we have a background, I would like to introduce you to the aim of the study. So the aim of this study is to develop a heap processing route for niobium-based transverse combustion chambers using isostatic pressing. So we'll study the heap response of different niobium powders and down select the heap process parameters and perform microstructure analysis to understand the fundamental differences between the niobium heaped microstructures. And then I'll assess the influence of powder characteristics on microstructure mechanical properties by understanding the impact of oxygen on measurements on the mechanical properties, and as well performing mechanical testing. So I would like now to introduce you to the experimental plan to familiarize with the procedure we used. We used 3 different niobium powders, respectively niobium mid-range, niobium coarse, and niobium fine. As we can see, there are different powder ranges. And then we have performed a detailed powder characterization on the 3 powders. After the powder characterization, we then have consolidated the powders using HIP, performed microstructure analysis and microhardness, which is very important to have a first understanding on the mechanical properties. And then we have performed room temperature tensile tests just on niobium mid-range. And after performing tensile tests on niobium mid-range, we have performed sieving operation on niobium mid-range, which will the sieving operation will be explained later on, the reason why we have performed them. Sieved mid-range powders were then consolidated, microstructure analysis was performed, microhardness, and also tensile tests. So now we'll move to the first relevant result. First relevant result concerns powder characterization, so in particular powder morphology and heaped microstructure. So if you can see from the 3 backscattered micrographs, we see that the 3 powders have different size ranges with a particle shape, which is rock shape, typical from hydride-dehydrate process. If we now look into the microstructure, the first important thing we can see is that the 3 microstructure have near to fully dense microstructure. This means that we have successfully selected the right heap parameters. And also on the first relevant result is the average grain size. So we now, as you can see, we now direct correlation between a particle size and average grain size, with a fine powder showing the lowest, the finest microstructure, and coarse powder showing the coarse microstructure. This is an important point because we can say that we can tailor the microstructure by changing the powder particle size. Another more relevant result coming from the microhardness result, microhardness tests. In fact, there is a variability between the hardness, with niobium fine experiencing the highest hardness, followed by niobium coarse and niobium mid-range. In this case, we found out that the most important parameters influencing the microhardness is the oxygen content. In fact, niobium mid-range had the highest oxygen content, followed by niobium coarse, and with niobium mid-range having the lowest amount of oxygen. So we can say that oxygen levels are more important than than grain size in achieving higher strength. Another worth noting result is that Rhodes C103, that niobium fine and niobium coarse have higher level of hardness if compared to Rhodes C103. After performing microhardness test and having an initial overview of the strength of the material, we performed tensile tests. So room temperature tensile properties were performed on high-sipped niobium mid-range. The reason why we performed the room temperature tensile test on niobium mid-range is because we wanted to understand what are the room temperature tensile properties of low oxygen niobium, because then we can improve increase the oxygen levels and try to increase the tensile properties. Niobium mid-range experience high level of yield strength if compared to literature and to Rhodes niobium, high level of UTS, and it's important to note that of course we had a drop in elongation, but still we have a good ductility with an elongation above 40%, which is witnessed as well by the fracture surface having dimples, which are characteristics from ductile fracture. However, we're still not matching the requirements of 260 megapascal of yield strength. So what we have to increase now the oxygen levels in order to increase the strength. So to increase the oxygen level, we have performed the sieve operation on niobium mid-range. Why sieving? So if we sieve a powder, we then achieve a higher surface to volume ratio for our powder. Achieving higher surface to volume ratio means that we have more contaminants on the surface of the powder. In this case, we have more oxygen on the surface of the powder. In fact, we managed to increase the oxygen level from 310 ppm to 756 ppm on the sieved powder. So more than 400 ppm just by a sieving operation. And we managed as well to increase the hardness from 104 to 135, so around 30 Vickers more of hardness. And also, as stated before, there is also in this case influence of particle size on the grain size. So average grain size was 53 for niobium mid-range and decreased as we decreased the particle size on sieved niobium powders. So then we try to understand the room temperature mechanical properties of niobium sieved to see if we had an improvement in strength. The results are very encouraging because we had a clear increase in yield strength, which is around 200 megapascal, much closer now to the target of 260 megapascal for C103. We have increased as well the UTS, and interesting to note is that elongation has dropped just by a small amount, which having also in this case higher an elongation much higher than 40%, representing a good level of elongation, an excellent level of elongation for this application. So by simple sieving operation, we managed to increase the oxygen level. So in conclusion, to conclude the work, we can clearly say that HIP was successfully performed on pure niobium powders, on all the three different niobium powders, and also on sieved niobium powders with a near to fully dense microstructure, highlighting that the process parameters were successfully selected. Microhardness and mechanical properties are strongly affected by oxygen content, which is a dominant effect to increase the dominant variable to increase the oxygen, the strength of the material. Dominant if compared to the grain size, which also has some importance. Then by a simple sieve operation, we increase the microhardness and also the yield strength of niobium powders, which now is approaching 200 megapascal, closer to the required levels for C103 niobium alloy. However, higher oxygen levels are required to meet the room temperature mechanical properties of C103, but we are getting closer. Another important point is that future work are required to identify the creep properties and more in general, the high temperature mechanical properties of niobium. Because as we know, the presence of a pure metal without, for example, precipitates or stable oxides, as in C103, would probably compromise the high temperature properties by and the pinning of grain boundaries during creep. So I would like now to thank you all for listening and for your time, and I'm happy to take your questions.
Many thanks, Alessandro. So just have a quick look at the Q&A box. So if you do have any questions, please feel free to pop them into the chat box. So whilst you're waiting and you're sort of gathering your thoughts, I can make a start. So you've tested the mid-range sized powders and sieved them. Did you test the fine range powders just to see where the mechanical properties, does it still show an upward increase, or is there a degradation in performance?
Yeah, we haven't tested, we haven't performed room temperature tensile tests on fine because of two reasons. First reason, we were quite sure that the material would experience a brittle fracture. Second reason, unfortunately, we had very low amount of fine particles. But what we have done, because of lack of time, I couldn't show it. We have made a simple model to try and understand how the oxygen level can impact the yield strength. And yes, the niobium fine would experience a much higher level of yield strength if compared to the 260 megapascals of the required application. But yes, they would experience very low elongation. I think by performing a sieving operation on the powders with a smaller sieve, because we use now 63 micron sieve, we would probably be able to achieve those levels of yield strength.
Okay, understood. I'm not sure if there's any other questions come through from the chat. Probably got time just for probably one more. So just a question on sort of the practicalities, the scalability of this approach. If you're now having to, obviously in a lab-based environment, you're controlling parameters. Yeah. It sounds like you've identified the critical parameters which affect the mechanical properties. So do you see any problems in scaling that process and having repeatability in material behavior?
This is a very interesting question because it depends on the powder. Okay. So if you have reliability on the powder manufacturer and on the consistency, then the process can be reliable as well. For example, because we increase the oxygen level by just performing sieving operation. So if we have consistency with the initial powder to start with, then the process can be consistent as well. Another approach that can be used and was not used in this study is to perform heat treatment on the powders. This is another approach, but I think that by performing heat treatment, we have more variability than performing a simple sieve operation. And furthermore, it's more expensive and more and there are more a higher leading time associated with heat treatment, of course.
Okay, excellent. Well, okay, thank you. I think that's probably, we've just come to the end of the time for this session. So I presume, Alessandro, you'll be around for the rest of the day. So if people want to send a direct message, they can follow this. Of course. Brilliant. Okay, so thanks again, Alessandro.
Thank you. Thank you.
Okay, so let's now move on to our second speaker. And this is, I'd just like to introduce Mohammad Alghfeli. So hopefully I've pronounced your surname correctly, Mohammad. So he's a second-year PhD student with the University of Cambridge. And his presentation will be on an approach to enhanced high-density polyethylene nanocomposites. So Mohammad, if we can pass it over to you.
Hello, good morning, everyone.
Morning.
Okay, can you see my screen?
Not at present, no, it hasn't updated on my side.
1 second.
Alessandro, could you just stop sharing your screen, please? Thank you. There we go. Lovely.
Okay. I think it should be okay now, right?
Just waiting for it to update on my machine. Okay, I can't currently see your presentation, so...
No, it's not loaded yet, Mohammed.
You just click on share screen, right, in the bottom?
Yeah, so share screen, and then you have to select which application you want to share or which screen you need to share. There we go. Excellent.
That's good. Yeah, full screen. Excellent. Okay, Mohammed, over to you.
Okay, perfect. So you give the introduction of who I am, and officially I'm a second-year PhD, but unfortunately, due to COVID, we had a lot of time missed in the lab, probably like 6 to 8 months. Anyways, I made this presentation quite short and simple so that, you know, everyone is in a different major so that you can easily understand it. So first of all, the research motivation behind this PhD is it's an industrial issue. I worked as an intern for ADNOC 3 months before I started my PhD. And we were looking in the research and development departments at all the critical issues. And one of the most important issues was the pipeline corrosion. So we did some research and we found out that there is so much potential in the HDPE thermoplastics to be improved. There's a lot of research done, but there's still gaps that need to be filled. So we decided to take on this project. So the research impact is that we anticipate that this HDPE as a non-metallic liner will highly contribute to the reduction of corrosion in pipelines and decrease the life cycle of materials, leading to a lower maintenance costs. So I'm going to take you through the process of how we are planning to prepare this enhanced HDPE. So the main objective is, so we're going to go through an entire evaluation cycle of the most promising strategy to an enhanced HDPE. As I said, there's some research out there that has done it, but not quite effective. So we will look at the preparation of an enhanced HDPE from different aspects, and then we're going to assess if it's manufacturable so we can use it in the industry. So the expected level is that we expect by the end of the PhD to successfully provide design rules and guidelines on the influence of nanofillers, specifically nanosilica, on the processing and properties of HDPE nanocomposites, and the most suitable techniques to improve the compatibility and to produce the enhanced HDPE. So first step is, before going to the HDPE itself, so we want to improve the HDPE. So the first step is finding a suitable filler. Okay, so fillers in general that we can use are inorganics. So they're not compatible with HDPE. So we need to include the term of surface functionalization. So basically it's the chemical modification of the material surface using different strategies. We're gonna go through them in this process, in this presentation. So in general, in our PhD, we're going to use commercially available silicas that are already functionalized. We might further functionalize them if needed, but in our first stage, we're going to use commercially available ones and see how they proceed. We're going to make several different assessments and see if they are suitable for being used for HDPE. So this is just a quick demonstration of how the surface functionalization works. So as you can see, the figure down, it involves the reaction of OH groups with certain silanes like TMS from HDMZ, which is hexamethyl disilazane, which converts the surface from hydrophilic to hydrophobic. So there's different routes to synthesize the silica, liquid and gaseous, but as I mentioned, we're going to start with commercially available ones because we're planning in the long term to have this as an industrial project. And if we make our own silicas in the lab, it might be more challenging to proceed through it in the industry. So there's different synthesis routes for the polymer nanocomposites once we finalize the fillers. The most common one is the melt mixing, the first one, direct mixing, melt mixing, or it's also called melt compounding, where we mix a polymer with nanofillers above the softening point of the polymer without any solvent. It's commonly used because it's simple, but it might have some drawbacks. So the first approach is stage one, as I said, the nanofiller. This is a route if we are going to design the nanofiller, but in our idea, we're going to use the commercially available ones from different series of functionally available ones, and we're going to assess them using TGA, thermogravimetric analysis, dispersion testing in different solvents, and we're going to use NMR to thoroughly study the surfaces and the properties of the different fillers to have an idea if it's possible to incorporate them in HDPE. So as I said, people previously have done this, but they haven't got into high loadings, high loading weights of these fillers in HDPE. So the more loading weight we have in the system without any processing penalty, we are supposed to have more improved properties. So this is the stage 2. Once we have the filler, once we know the most compatible or suitable filler for HDPE, and after we disperse them in different solvents, we're going to try incorporating them in HDPE using solvent-based methodologies. So it's going to be basically, let's say we have 4 different commercially available silicas at different loadings. We're going to indicate the best possible loading without processing penalties, and then we're going to prepare groups of nanocomposites. So it's going to be, for example, 4 groups, and each group is going to have several samples, and we're going to characterize them to determine which of these candidates is the gives the best improved properties without processing penalties. And then we're going to take it further steps from there, and then we're going to assess if it's manufacturable or not. So basically, looking at these 2 figures, our ambition over here is the one on the right, to actually, the plan is to, so HDPE is a commodity plastic. We want to increase its properties to be somewhere in this figure over here, but with a reasonable cost, which is going to be adaptable by the industry. So in general, we don't want to change it to a complex structure, but we want to modify and further understand the interfacial chemistry between the fillers and the polymers, so that we can easily incorporate higher filler loadings and achieve improved properties. So this is these are some findings. As I said, we didn't have enough time to actually work in the lab. Things are progressing well now. So these are some of the studies that are really close to my PhD of an author called D'Argato. So he has used the melt compounding strategy to functionalize R974, which is it's a functionalized silica with D species. He has incorporated them in HDPE in 2 different loadings, and he has found that there is no influence on the melt flow index, so processability is fine. And for 2% loading, can be shown here that several properties have been improved without any processing penalties, which is a good sign. And so this is a further slide representing how the recent literature of the R974, which D'Argato did, improved properties. So basically, there is so much potential in what these functionalized fillers can do and the outcomes of the HDPE, but there's still some gaps on how to get the best compatibility and higher filler loadings without any processing penalties. So basically, the scope of this PhD is to take it from step 1 on having these functionalized fillers and characterizing them using all the different techniques like NMR, rheology testing, and TGA, thermogravimetric analysis, and Hansen solubility parameters to actually study and understand the interfacial chemistry, so we can know, I would say, the best technique to incorporate them in HDPE without processing penalties. And in conclusion, so I covered the importance of chemical compatibility as having more compatibility between the filler and the polymer. You would be having more filler amounts in the polymer. Therefore, we're going to have a higher property improvement. and has been proven, as I showed you, that HDPE has significantly increased the critical properties. But as I said, they went up to just 6 or 7% loading. So our goal is to, I would say, reiterate what they did, but to take it from different characterization methods to seek if it's possible to go up to, I would say, 20 or 25% loading to get the most out of these fillers, and at the same time have no processing penalties. And then after this, after we have an overall understanding of the interfacial chemistry and the compatibility, and we've got good compatibility between the filler and the polymer, we're going to further seek manufacturing the HDPE and taking it to the next level for the industry. And thank you for listening.
Excellent. Many thanks, Mohammad, for your presentation. So again, if you do have any questions, please don't hesitate to use the Q&A function within Zoom. So just whilst people are gathering their thoughts, I don't believe there's any questions just yet. So obviously it's very clear you've got quite a large sort of experimental campaign to do. And I can appreciate there's a huge number of design variables for each of the different techniques that you're going to be exploring. So my question is, it just picks up on one of the points that you mentioned about the novelty of your work. And I believe it's related to the compatibility between the filler and the matrix and developing new techniques to be able to measure that. So my question is, you're going to be performing a large number of experimental lab-based tests. Can you just provide some insight into what are your thoughts for assessing the compatibility between the filler and the matrix to allow you to have some form of quantitative comparison between these different approaches?
So first of all, so as I said, a lot of research papers have been done in this area, but they have been looking at different aspects separately. So some publications are just focused on NMR, some quantitative analysis showing the surface chemistry of the fillers before and after surface treatment. Some of them just focused on rheology. So basically what I'm doing is gathering all the possible characterization techniques that indicate that we have better compatibility. So for example, I would say, let's say talk about the rheology. So we're going to disperse the functionalized silica in different solvents, and we're going to generate rheology curves to see when does the viscosity increase at what certain percentage of these loadings, so we can understand the limitations of the functionalized fillers in these solvents. And so since they are commercially available and they're functionalized, we can actually further functionalize them if they have certain limits, if you get that what I mean. So this is one of the approaches. The second approach is enhancing solubility parameters. It's like it's an experimental technique to know whether certain liquids are gonna disperse in several solvents without having any processing penalties or sedimentation. And also we might actually, I didn't focus on it, but we might use a electron microscopy to actually look after we disperse the fillers in the matrix on how good the dispersion is in the matrix, so we can understand our compatibility more.
Okay, no, thank you for that. It's a detailed answer. We've got time probably for one very quick question just come through on the chat. And the question is, do you have plans to chemically link the siloxane into part of the HDPE backbone?
Not at the moment. So we want to, actually, as I mentioned, we want to make the most out of the least, I would say. So we would try these functionally available ones and incorporate them in different solvents. If it's possible to go in high loadings then and with minimal functionalization, then there's no point of making the structure more complex because it might affect the processing. So we would like to actually seek first if it's possible to do it in the easy way, and if not, we might incorporate further strategies to improve the compatibility.
Excellent, many thanks, Mohammad. Okay, excellent. We'll just come to the end of the time for this particular slot. So just again, I'd like to thank both speakers this morning for a really good start to the composites and polymer session. So we're just a little bit over time. I think we're due now for the first break. So we're going to be returning again at 11 o'clock for one of the first presentations from the core research program by Chris Worrall. So yeah, please go and stretch your legs, get yourself a cup of tea and coffee, and we'll be returning at 11 o'clock UK time. And again, if you do have any follow-on questions, please don't hesitate to get in contact with the speakers this morning. Okay, so we'll see you very, very shortly. Okay, so welcome back. I hope everybody had a good break. So welcome back to the Composites and Polymer session. So what I'd like to do now is to introduce Dr. Chris Worrall from the Advanced Composites and Adhesive section, and he's based within the Polymer Composites Technologies group here at TWI. So Chris will be providing the first of several presentations on the core research program, and his title of his presentation will be the Preliminary Mechanical Properties of Thermoplastic Composites Containing Multiple Pierced Perforations. So Chris, over to you.
Thank you, Kevin. Now, I always wondered about holes. Are they real? How can something exist just by being defined as the lack of something? But the French engineer and architect, Robert Laricolet, put this nicely when he said that the art of structure is where to put the holes. But what if we want to put them everywhere? What if we want to perforate? Is it worth it? How do we do it? And why would we want to do this? So this idea started a core research program project at TWI a few years ago. Now the story actually starts not long after I joined TWI 11 years ago with a former project on the machining and mechanical fastening of composites. And at the end of that project, we decided not to focus on machining holes in composites, but finding other ways to make holes in composites. So there's been several projects leading up to this one, and the idea is continuing in other projects in the future. So this project, we were lucky enough to have an industrial mentor, Dr. Amir Rezai from BAE Systems. He was the mentor of the previous project where we developed the tap process for perforating. And he wanted to continue because of the applications for this technique in the defense sector. We also benefited from internal mentors, Paul Burling, before he retired, and then Dr. Tyler London took over afterwards. And the support of an NSIRC NSTOC project and student, Faranak Bahrami from Surrey University. So what is the industrial need? Why would we want to perforate composite materials? Well, there are a lot of applications where this may be useful. One in particular is the leading edge of aircraft wings, where we need to de-ice or prevent ice forming. And this is currently done. One of the ways it's done is to perforate the leading edge and then allow anti-icing fluid to squeeze out when it's needed. So a lot of very, very small holes. Engine noise is also very important. Jet engines are very noisy, and so the inside cowling contains a perforated panel that helps to absorb the engine noise. Noise is also a problem with landing gear. As the landing gear is deployed, it creates turbulence, which creates noise, and this only happens at takeoff and landing, generally where there is a high population density that gets very annoyed. A relatively new concept is the hybrid laminar flow control, where we perforate the control surfaces of an aircraft, and then we manipulate the airflow through these holes to create smooth flow on the surface and improve efficiency and reduce fuel burn. Another application is blast protection. So blast protection structures can be partially perforated that act as a pressure bypass valve. So they allow some of the pressure wave to go through and protect the rest of it and protect the occupants or the structure on the other side from shrapnel and blast damage. And finally, in the oil and gas industry, tension leg platforms, these are also being perforated now to allow the flow of seawater through them to prevent damage. So there's clearly an industrial need. There's a demand for perforated panels, and metal panels are relatively straightforward to perforate. They can be stamped, they can be drilled, milled. It doesn't really damage them very much at all. We're just removing material. But with composites, it's a different story. It can be difficult to machine them. There can be a lot of wear on the tooling, and we're cutting the fibers that we spend so much time and effort making continuous to get the best properties. And then we cut them when we make a hole. So can we make holes without harming fibers? Is there a way? Well, there is, and actually, if we go back a couple of 100 years, sailors used to do this. The sails were attached to the ships with ropes through holes in the sails, and rather than cutting a hole in the sail, they used a stabber or awl, pegging awl, to pierce a hole, displace the fibers sideways, and then they could attach the sails without reducing the strength. So all we're doing is recycling an innovation from several hundred years ago, but adding a bit of matrix material in there into a composite. So these project objectives of this CRP project were, first of all, to develop a multiple thermally assisted piercing technique for thermoplastic composites. So how are we going to make the holes in the composite? We're then going to characterize the composite material containing an array of perforations through basic mechanical testing. And then we're going to try some finite element analysis and see if that will help us get extra value by being able to predict the properties of these perforated panels. So starting with manufacturing, at the start of the project, we designed and manufactured this perforating jig. It looks a bit like an instrument of torture. It's a bit complicated because there's an array of 10 by 10 pins that can be, their positions can be adjusted and they can be removed to produce different patterns of perforations. So how does it work? How do we make these perforated panels? Well, again, it's relatively straightforward. We take our thermoplastic matrix composite and we heat it up by clamping it under a rig, applying some heat by whatever means we want to. In this case, it was conduction in a press. And once it's up to the temperature, so above its TG or around its melting point, we can then press on this perforating tool onto the surface, pushing the pins into the thermoplastic matrix, displacing the fibers sideways, making our holes. And then if we wait a little while for it to cool down again, we have our perforated composite laminate. So we spent a lot of time at the beginning of the project developing this process. I'll show you some of the first and last trials later on in this presentation. But once we'd got to a stage where we could make good quality laminates with an array of perforations, we moved on to mechanical testing. There are a lot of different mechanical test techniques you can use to measure a lot of different mechanical properties. So we started with open hole tension because we thought that maintaining the fiber length would give us a strong advantage here. We also wanted to look at open hole compression because this is very important for the aerospace industry in particular. And finally, we looked at Iosepescu shear, a shear mode, just because it was a little bit unusual and we'd never seen anybody doing this kind of test on composites with holes in them. So we started with open hole tension. Now there is a standard, an ASTM, there's a BSE and ISO as well, for open hole tensile strength, but it only contains a single hole of 6 millimeter diameter. There are no standard test methods for multiple holed materials. So we're not starting off on a very good foot here. We're having to invent our own standards and test methods. So we took this standard and modified it slightly. We kept the same geometry, we kept we changed the hole diameter, and we changed the number of holes. But in all the tests, we kept the same hole spacing in the work that I'm going to present to you today. So we put our perforated panel in test coupon in the machine and we pull it and we measure the strength. And here's a summary of the results. So the gray column on the left is the unperforated. So this is our perfect composite. The blue column in the middle is our perforated coupon, which is just about the same mechanical properties. And then on the right is the drilled version. Now with the drilled version, we were very careful to be fair and to produce a very high quality drilled hole, because the quality of the hole can affect the drill, that can affect the mechanical performance. So from open hole tension, we can see we're getting a very clear benefit over making these holes by drilling. So that's a good start. And again, if we look at the basic raw data, the load displacement curves, we can see that the pierced and the unperforated, and in fact the drilled, they're all behaving in about the same way. So there's nothing unusual going on. So if you move to open hole compression, again, there are no standards. So we have to modify the open hole compression test method by adding more holes. This time we get a different story. Again, on the left is the unperforated, unholed composite. In the middle with red is the perforated, and we get a big reduction in the strength. And it's even lower than the drilled coupons. So we're getting a lower strength. And again, if we look at the load displacement curves, there's nothing unusual happening. We're just getting a lower strength value. So why was the strength so low? Why was it not what we were hoping for? Well, if we look at the fiber orientation around the hole, we can see that the fibers are distorted. They're bent around the hole. Now in tension, this doesn't really matter, but in compression, this can lead to buckling. And in fact, when we look at the micro sections of the composites after compression testing, we can see exactly that. So in effect, we're introducing a weakness into the composite in the compression loading mode. The third test was the Ossipescu shear. Again, this is an unusual test, and there are no test methods for it. There's a test for an unperforated coupon for composite materials, the 5379. So we tried to use the same method, and we added 2 perforations in the center between the 2 notches, just to see what would happen. Now again, if we look at the results, I don't have the data for the unperforated composite, but on the left this time we've got the perforated, and on the right is the drilled. So we can see again that we're not getting as good a performance using this technique compared to drilling. And that was a little bit confusing because we were expecting to have at least the same performance, if not better, because we're not cutting the fibers. There are more continuous fibers through that central region that's being loaded in shear. Now, if we look at the load displacement curves, now we can start to see something unusual. We're getting a different behavior. Rather than the drilled coupon showing the conventional increase in load, a slight yielding and then continuing until the rig bottoms out. We're now getting this local yielding and a reduction in strength at about the same value as we did before, but we're reducing the strength during the test, and that never recovers. So what's going on? Well, if we look at what we have in this test, this is a magnified image of the center between the notches, 2 holes, and the fibers running across. There are fibers running in the other direction, but for this explanation, let's concentrate on the ones crossing through the notch. Either side of the holes, the fibers are cut because of the drilling process. So this is what we have, and we're loading this in shear mode. And with the perforated pierced material, the fibers aren't cut, but they're displaced around the holes, so they're continuous. So actually, if you think about it, when we displace the right-hand side downwards, the fibers, they either have to break or they have to transfer that motion, that load, that displacement all the way around the hole. So as we push down on the right, we're pulling right on the left. And because this is clamped on this side, and both sides are clamped actually, we're introducing some unusual loading cases. Another thing to bear in mind also is that as this happens, these fibers that are running around the hole, because they can't break or distort, they have to straighten under tension. And as they do that, they start to deform the shape of the hole. And as they deform the hole, they start to collapse the structure between the notches. So this is the explanation. We have some nice little videos showing displacement vectors from the digital image correlation test that we did. This basically shows you the direction and magnitude of the movement of a lot of points on the surface during the test. The right-hand side is moving down, as you'd expect, and the left-hand side is being pulled across. Now, this is for the drilled coupon, so we are getting some pull to the right-hand side. But if we look at the vectors, we can see that they're starting to curve down here. And also the magnitude of the vectors at the top is much greater than it is at the bottom. So we get a displacement gradient. So this is what's happening to the fibers in the drilled case. If we look at the pierced perforated case, again, we get the same kind of behavior, displacement down on the right. But now if you look on the left, all these points are moving horizontally. It's not until we get right close to the space between the notches that they start to deform. And also at the end of the test, if we look at the magnitude, we can see that the magnitude is constant. So we're getting a constant displacement of this side of the specimen. And this is because all the fibers are continuous through here. And as we move down, they're all being pushed across. The holes are being collapsed, which is why we're getting a lower strength. So I said that we would touch on finite element analysis. It wasn't the main part of the project, but it would provide some value. Now, one of the problems we have here is that when we change our composite by perforating it, we change the mechanical properties. So on the left is our unperforated, and on the right is our perforated around a single hole. So we start off away from the hole with our original fiber volume fraction and fiber orientation. But close to the hole, we have a higher volume fraction where the fibers are packed together. And we also have a different orientation. So spatially, we have a distribution of fiber orientation and fiber volume fraction, and therefore a spatially dependent set of mechanical properties. So we want to predict what these are so we can then exploit them in some mechanical modeling. The problem is that we have a problem of the number of fibers. If we take a small piece of composite, just in this 3 millimeter thick laminate, 50 millimeters square, there are 1.8 million fibers. They all have to have contact with each other during the perforating process. Matrix material is flowing between the fibers are moving around. It's extremely complicated to model on a fiber basis, so we have to make some assumptions. Now, one of the academic supervisors is a specialist in numerical modeling, and Tyler London, our internal mentor, he's also an expert in numerical modeling, who helped us out in developing the model you can see here, where we're showing the displacement of the fibers during the piercing process. And this is about as far as we got in this project. So we push the pin down into the composite, and the fibers move to the side. And we can get an idea of how those fibers are distributed, but there's still a lot of work needs to be done in the future. So that's a summary of the work done with the manufacturing, mechanical testing, and finite element. The question now is, how do we exploit this? How do we take it further? Well, first of all, if we look at what we delivered during the project, there was a literature review on industrial applications for perforated composites. There was the members report on the summary of the mechanical properties. We produced a multiple perforation rig that we can use going forward, and a basic finite element model that we can use to simulate the piercing process. There was a conference presentation in 2019 at Aeromat, the next year at ICCST, and then at ICCM in Australia. Presentation in Barcelona at the Nanomedicine and Material Science Conference, a talk at the TWI Eastern Counties branch meeting, and next month there's a presentation at the Composites UK Defence Sector Showcase, all based around the work from this project. So how can we exploit it? What can we do with this? How are we going to get industry interested? This is where the combination of the manufacturing, the testing, and the simulation is important. We can take a composite material and we can perforate it. And then we can look at the fiber orientation distribution. And then we can predict what the mechanical properties of that new composite are going to be. And we can tell whether it's going to work in our application. On the other hand, we can take the application and look at the loads required and the deformation mechanisms and the stresses, etc. And we can start off with a model and work backwards to work out what perforation structure is necessary to achieve that. And once we know that, we can take the step backwards again and work out how to achieve that by the perforating process. So these are two ways that we can exploit both the mechanical, both the manufacturing and the simulation. Now, in terms of follow-on projects, there hasn't been any single client work on this yet, although there have been a few opportunities, especially from aerospace and also defense sectors. But we do have another PhD project at Brunel University. This is another NSIRC project, Man-Chi Chung, who started in January. And she's looking at exploiting the simulation capabilities of this project in producing a novel metal to composite joint for naval applications. And we also have another CRP proposal at the moment, looking to exploit this technology in an automated 3D welding capability. So were we happy with what we achieved? Well, if success is defined as the ability to go from failure to failure without losing enthusiasm, I think so. because if we look at how we started, the first perforated panel we made looked a bit like, well, it looks like my dog's breakfast. It's not very good at all. But by the end of the development process, we found a way of making very nice quality perforated panels. So ultimately, yes, we were very successful. And I just want to leave you with something to think about, and that's in the future, when you hear about soldiers surviving IED explosions, when you're living near an airport and you're amazed by how quiet the aircraft are, or when you take off on a holiday and it's snowing and icing, and yet the aircraft doesn't have to stay on the ground. Maybe, just maybe, that's all because of some of the work done in this CRP project. So I want to leave you now with an image of the student, Faranak, holding up one of her perforated panels, showing an animation of an X-ray CT scan through the laminate, showing the position of the fibers as they're displaced. So I think we just about have enough time for a few questions.
Yeah, that was an excellent presentation. Thanks, Chris. So let's have a look at the Q&A. So if you do have any questions, then please don't hesitate to put them in. Okay, so whilst I don't think I can see any questions at present, so whilst people are gathering their thoughts, just a question out of my own curiosity, really. In terms of how critical do you think the density of the holes will be on the mechanical properties? At present, it looks like you've obviously got quite a large displacement between the holes in those standard tests. Is it something that you've looked at, or is it something you plan to look at in terms of increasing the density and how that potentially could affect performance?
Yeah, it is, and it's a very good point. If you think about it, we're not adding or removing fibers.
Mm-hmm.
So ultimately, it shouldn't matter. You can fill the plate full of holes and you've still got the same number of fibers carrying the load, in tension at least. The problem we thought of at the beginning was that you can think of these fibers as streamlines flowing around the holes. And as the holes get closer and closer together, because the fibers are strained elastically slightly during this process, there's less motivation for them to remain in their position between the holes. So they end up running around the outside of one hole and staying in a straight line until they come to the end. So they don't produce the right pattern that we're looking for. Now, whether this is significant, whether it affects the properties, I don't know. It could have a beneficial effect on the compressive properties because we're removing that waviness that's causing this weakness. But we did look at varying the hole spacing for a constant hole diameter from 2.5 times the diameter to 10 times the diameter. And we didn't see any really significant difference in the mechanical properties. I think we'd have to go smaller or closer together than 2 hole diameters apart before we start to see this. But we certainly do start to see evidence of fibers being displaced between the holes caused by the proximity of the holes and the strain energy in the fibers.
Excellent. Well, thank you for that answer. The question has come through on the chat, and the question says, how about the fatigue strength properties?
Oh, that's a good one. And the answer is, I don't know. We didn't get that far in the project. It's something that would be very important if we were looking at aircraft applications or even tension leg platform applications. I don't see any real problems. We understand the behavior of composites in fatigue as a function of orientation, as a function of volume fraction. So we could argue that as that's all we're doing, we're changing the orientation and the volume fraction, it should be okay. It would be interesting to see, though, whether there's any difference in the viscoelastic heat generation in the thermoplastic composite because of this distribution, and whether that has any effect.
Okay. Excellent, thank you. Just having a look at any other questions on the chat. Okay, there's a thank you from from Kian, so thank you for the answer, Chris.
Kevin, there is a question in the Q&A.
Okay.
It says, do you know if these perforated thermoplastics have applications in the oil and gas industry?
Oh, well, the one I mentioned at the beginning was a tension leg platform, and I popped that one in just to give a nod to the oil and gas industry. I don't think that using this kind of approach is going to be successful for that. The whole point of this is that we're using small diameter holes. It's the whole concept is based around a hole diameter to hole spacing ratio and the area that you have to heat. So this works well for small holes. The tension leg platform would work better for larger diameter holes. But there are certainly some potential applications that we're looking at through the Non-Metallic Innovation Center, where we're using a similar idea for thermoplastic pipes. So watch this space.
Thank you.
Okay, excellent. Okay, so it doesn't look as though there's any other questions. So thanks again, Chris, for your presentation, your time, and hopefully, if you're still around for the rest of the day, if any other questions pop through, people can get in contact with you direct. Is that okay?
Sure, I'm happy to.
Excellent. Okay, thank you, Chris.
Thank you.
Okay, so we're just a few minutes ahead of time, so just gives me the opportunity just to welcome everybody. So if you just joined this session, so I'd like to just welcome you to the Composites and Polymer session. So this particular session is sponsored by the Brunel Composite Center and Teesside University. So we have two speakers that will take us up to lunchtime, and the next speaker is Minghui Wu. And again, I hope I pronounced your name correctly. So she's a third-year PhD student with the University of Surrey, and her presentation will be looking into assessing the life cycle costs and environmental performance of composite materials in aircraft applications. Okay, so if we can pass over. Are you able to share your screen? Perfect.
Is this the presentation mode?
It's not. Yes, it's not full screen.
Oh, okay. Sorry. How about now?
Yes, it's just updated. Yeah, that's full screen now. Perfect.
Okay. Hello everyone. My name is Minghui Wu. I'm a third-year PhD student with Surrey University and NSIRC. It's my pleasure to share my PhD study. My topic is assessing life cycle costs and environmental performance of composite material in aircraft application. My presentation includes 4 parts, which is project introduction, methodology, results and discussion, and the last part is conclusions and future works. I will start with the introduction. Nowadays, we pay more and more attention to reducing the emissions in order to improve and protect the environment. European Union had launched a program which is INSPIRE 2 to cut the aircraft emissions. Under this program, sub-project named the thermoplastic on door, which aims to manufacture an aircraft door using composite materials to replace the conventional aluminum materials. But there is no corresponding environmental and economic assessment on this door. So in this case, my research aims to bridge this gap by assessing environmental and economic impacts for the composite door. In addition, my research also conducts a comparison analysis between the composite door and the aluminum door. That's the background. Let's move to the methodology. To assess the economic performance of the product, I use life cycle costing method. This flow chart shows how I conduct this analysis. The first step is setting up the scope and the system boundary. And then the cost breakdown model is built based on the production activities. And thirdly, calculate the total cost and then perform sensitivity analysis and to identify the effectiveness of key factors which influence in economic impacts. And last is the results interpretation. For the environmental impact assessment, life cycle assessment method is used. This model I built is based on the standard ISO 1440 and 1444. And this analysis is carried out with the support of the Thamasha software. The industry data is used in this model. So those data is not available. The secondary database, such as the eco-event database, is used. And during the mass production analysis, we should consider the labor hours will reduce as we produce more products. This is mainly because the improvement in workers' skills. So to capture this improvement, I use the learning curve method as shown in this figure. This theory says each time the number of units produced doubles, the cumulative average time per unit is reduced by a constant. So in generally, the mass production process can be divided into two stages, the learning period and the standard period. The direct labor hours required to produce one unit decreases rapidly in the learning period and slowly in the standard period. In my research, the labor hours required at the beginning of this standard period is considered as the minimal time required producing one unit by a fully skilled worker. This unit, N, is called the endpoint. I developed a method to calculate the endpoint. So you can see N is calculated as the smallest integer, and that satisfies this inequality. And that's the brief summary of the methodology I used. And let's move to the results and the discussion. In this case study, for the LC, the life cycle costing results, I only considered the recurring cost as the data limitation. So the total cost occurred is around 77K euro, including cost of material, labor, energy, and consumable. It can be seen that the most significant cost contribution is caused by labor at around 63% of the total cost. In the mass production, 87% learning curve slope is applied to estimate the direct labor hours of future unit. So we can see the unit 40 is the last goal produced before the learning period came to an end. And so we can see the contribution of labor cost in unit 40 has reduced to 45%, and leading to the reduction of the total cost to around 52K euro. For life cycle assessment results, and the results and the emission is aggregated for life cycle impact assessment using the impact 2002 method in Thamasha. So this network diagram obtained from the Thamasha, it shows the total environmental impacts produced by each process. So each box presents the process, and the arrows present the flows between the processes, and the thicknesses shows the contribution to the environmental load generated by each process. So from this result, we can see the energy appears to be the hotspot. After life cycle costing and the life cycle assessment, I also performed the sensitivity analysis to study the influence of production locations and the composite waste treatment rules on the environmental impacts. But here I will not go details as time limit. And the same assessment also applied on the conventional door. And the results compared with those for the composite door. We can see the left figure shows the comparison results in terms of the economic performance of the doors. And the vertical axle is the cost, and the horizontal axle is the aluminum door and the composite door. And the different colors means different cost categories. As mentioned, there are 4 categories I considered in total. That's material, consumable, labor, and energy. So from this figure, we can see the aluminum door has a better economic performance, about half of the cost of the composite door. In addition, the labor cost in each door is the highest. Then let's look at the red figure, which is the comparison of doors in terms of environmental impacts. And the impacts can be measured at the 4 damage categories, which is human health, ecosystem quality, climate change, and the resources. The blue bar is the aluminum door, while the orange is the composite door. So from this figure, we can see all the impact categories in the environmental performance are lower in aluminum door production. And the last part is the conclusion and the future works. And the key conclusions are as follows. Life cycle costing has been performed to estimate the economic performance of the door. And the learning curve has been analysis to predict the unit price of mass production. And the energy use is the hotspot in production system. Local regional supply chains are environmentally feasible than global supply chains. And the composite door may incur higher environmental impacts. I also discussed the possible costs and the solution. The current work mainly focuses on the production phase. In the future, I will continue on the use and the end of life phase to achieve a comprehensive analysis. Okay, thank you for listening. I'm happy to take any questions.
Yeah, many thanks for your presentation. Okay, so let's have a look at the see if there's any questions posted in the Q&A or the chat. Okay, not just yet. So so please feel free to use that facility. So whilst people are collating their thoughts, just a question for you. In terms of uncertainties, and obviously the numbers that come out from the costing for the aluminium door, how confident, or what's the uncertainty associated with the final cost that comes out? How do you take into account the uncertainties at different stages? Because obviously all those uncertainties in the input variables will have an overall effect on your final answer, won't it?
So I think that it will link to my validation, my results. It's normally used, it's necessary to validate this result through the publications, reports, and all expert consultations. For my research, this is a new product, and all the cost model, and I built based on the standard, and all the data I use have been validated by experts. Another, in addition, I also collect some cost estimation results from some literature regarding some other aircraft components. And the compression results also shows agreement with those publications, and that the labor cost and the material cost take up the majority of the total manufacturing protections.
Okay, so just a follow-on question. So in the development of the composite door, was it just a black metal approach? They just took the existing design and converted it into a composite equivalent?
Yeah, and this new door just a prototype, and it's a conservative design now. And this model I can use also can be used in the future when the design optimized.
Okay, so just a final one. So were there any, did you take into account the costs associated with joining? Because I can appreciate that the joining required in an aluminium or a metallic door will be completely different to a composite door. Did your model take that into account, or did you have information on that?
And for the new door, the composite door, the joining technique used the induction welding to joining the composite material. And for the composite and the metal parts in the composite door, we use mechanical rivets to join it together. Yeah, and I also compare. I also collected this data for between the. I also collected some industrial data for comparing the joining part.
Okay, thank you.
For the composite door and the aluminum door.
Okay, thank you. And I think there's a question that's come through on the chat, and the question says, how will you gather information for the end of life in terms of material properties? It says it may follow on. It says it may be difficult to weight them, although material experts may be able to help.
Yeah, the end of life phase is ongoing. Yeah, it's quite difficult to collect the real data from the companies, and this part I will use some secondary data, such as some data from publications and some database. And also I'm thinking to consult some experts and to know the detailed the process for recycling the composite and the metal material.
Okay, excellent. Okay, so many thanks for your presentation. That brings this presentation slot to an end. So if you do have any follow-on questions, please feel free to post direct messages and then they'll get answered. Okay, so thanks again. Okay, so now I'd like to just move on to our final speaker for this session this morning. I'd like to introduce Thamasha Dona. So Thamasha is a second-year PhD student with Brunel University London, and the title of her presentation will be The Design and Development of Composite Panels with Variable Thermal Conductivity for Lithium-Ion Battery Modules. So Thamasha, if I can pass over to you.
Can you hear me?
I can hear you, and we can see it's not full slides on your presentation, so we can still see PowerPoint. Yeah, that's great.
Thank you very much, Kevin.
Okay, thank you.
Hi, everyone. I'm Thamasha Dona, and my project is design and development of composite panels with variable thermal conductivity for lithium-ion battery modules. And my presentation also based on my PhD project. And I'm a PhD student from Brunel University. So when I'm considered about the background, we know in our day-to-day life mostly depend on the transportation. And when we consider about the transportation, That means mainly we have to consider about the vehicles, and vehicles normally we can identify fuel-based vehicles as well as hybrid vehicles, as also electric vehicles. However, due to the climate change and the lack of reliable supplies of hydrocarbons, the world is more into electric vehicles and hybrid electric vehicles. When we consider about the performance of electric vehicles and hybrid electric vehicles, normally the performance of these electric vehicles depends on their energy storage systems. In this case, the batteries are the energy storage systems. And when I'm considering about the batteries, in the industry, we can identify various types of batteries, lithium-ion batteries, lead-cadmium batteries, lead-acid batteries, lithium-sodium batteries. There are numerous types of batteries we can identify in the industry as well as in the field. However, lithium-ion battery is considered as the first choice candidate for the power source of electric vehicles and hybrid electric vehicles because they have like the low self-discharge rate, and also they have the higher energy efficiency, as well as also they have like the power to weight ratios, high level of power to weight ratios. So basically based on those advantages, normally in the hybrid electric vehicles and electric vehicles, they are using lithium-ion batteries. Therefore, my project is also based on the lithium-ion batteries. However, when we consider about the batteries and the electric vehicles, normally the durability of the electric vehicle basically based on the parameters like the factors which affects for the battery performance. So basically the formation time and the charge discharge times, and also the charge discharge temperatures, they are the basic parameters which affect for the battery performance. So if the battery is really good, then the performance of the vehicle is also really good. Therefore, we have to consider about those parameters, those factors when we consider about the vehicle. So when we, as I mentioned earlier, the temperature is the crucial factor of when we consider about the performance of the batteries, and therefore it is necessary to control the temperature distribution of the battery module for the effective performance, because if there is the uneven temperature, then there is the risk of having fires and explosions. So that's why we need to control the temperature. And when we consider about the existing methods, they have like the active cooling methods and also passive cooling methods. However, some of them are adding some extra masses to the system, so, and also adding some extra complexities to the system. Therefore, we have to avoid all these complexities. In my project, I have to build up the battery casing, which has the variable thermal conductivity in the different areas in order to remove this heat from the inside to the outside. So that is my project. So for the methodology, the first thing is I have to identify what is the heat transfer, the amount which is the heat generated inside the battery. And in order to find this one, how to build up the 3D single cell, and then how to extend this 3D single cell for the battery module. And I also conducted the heat transfer module for the different geometries by using this single cell and the battery module, and then experimentally validated everything by using the custom jig. So here you can see this is the 3D module for the single cell, and the module consists from 4 domains, including flow compartment, and for flow compartment consists from air and the active battery material. Active battery material is a kind of layer thing. That means they have like, it has like the cathode, anode, and the current collector and everything. That means it has also the different thermophysical characteristics in the different areas. So in the case of the simulation and in the case of modeling, I have to consider the effective thermophysical parameters when I'm considering about the active battery material. And battery connector is from stainless steel, and mandrel is the center part, and that is from the nylon. And this is the custom jig. Actually, the custom jig based on the different geometries. That means I already analyzed the different geometries and finally identified like like the 19 heating elements of the hexagonal arrangement is really good. So the custom jig based on the 19 hexagonal arrangement, and it was conducted for the 3 different scenarios I will later describe. And this is the jig, and the jig made from the heating elements, not the batteries, but these heating elements also have the same characteristics as the batteries. And this is the power supply and the electric circuit, and it has like this steel support also. And when I'm considering about the 3D simulation modeling, the modeling is developed basically using the CFD as the CFD model using COMSOL, and the energy balance equation is developed by considering the energy conservation laws and the volumetric heat generation. And when we consider about the battery cell, it has like the 3 different heat generation methods, like the heat is generated because of the resistive heating, and also because of the electrochemical polarization, and also the enthalpy change. So these are the 3 factors for the heat generation. And by considering these 3 heat generation methods, the volumetric heat generation is developed. And by using the this slide, we have like total accumulated heat, and this is the heat which is transferred from the coefficient convection. So this is the equation that I use in the single cell modeling, and this single cell model then extended to the battery module, and also use the air supply, which has 1 meters per second of velocity. And so that is the thing of the modeling. And in the experimental validation done for the cylindrical heating elements, and his cylindrical heating elements also have the, not the same characteristic as well as the batteries, but it also has the same dimensions as the batteries, like it has the same radius of the battery cells, as well as it has the same height of the battery cells. And in order to replicate the batteries behavior, like the charge discharge thing, I supply the discontinued power supply, like the power is supplied from like discontinuation. So that is the way that I replicate this the battery and the heating elements as the equivalent to each other. And to emulate the operation of the battery module, 19 heating elements were used and initially conducted for the single heating element, and then extended it for the module with 3 different intercell distance arrangement. Like I will later describe what are the intercell arrangements that I use. And so this is the experimental validation. When consider about the results, these results basically based on the simulation. First thing is I have to identify what is the geometry that I'm going to use. So firstly, I simulated for the battery modules for like the arrays, like 1 into 19, and then 1 into 24, and 3 into 8 scenario, and 6 into 4, and then the 19 hexagonal arrangement. When consider about the heat transferring aspects, when the battery became shortened, the module became shortened, the heat transferring is really good. And in terms of these arrangements, we can see the 6 into 4 arrangement is really good when in terms of the cooling capacity. However, both in terms of cooling capacity as well as the space utilization effect, the 19 cells hexagonal arrangement is really good. That's why I use that one is also for the investigations. And then the temperature distribution results, these temperature distribution results also analyzed by considering the cell distances. And first we conducted the simulation without any gap between each other, because I just want to see whether there are any effect from the air gap, and also then conducted with the standard gap scenario. That means each battery modules, normally each battery cells has like the intercell gap between 0.0 to 5 millimeters. So that is the gap. So that is the standard gap. And then I model for the double gap scenarios. So when the modeling happen, it can obviously see the central one has the highest temperature, and for 3 different scenarios that is the common. However, the temperature is really low. The temperature distribution is really low for the double gap scenario, and that means there is the effect from the air gap for the temperature distribution as well. And these simulation results are experimentally validated, and it can be seen for the single cell, the really good agreement I can see between the both experimental and the simulation. And when I'm consider about the module, is also it has like the really good compatible with each other for the, because I did all the experiment and the simulation results for the air cells, but since this one, everyone has the centered one has the maximum temperature. They specifically consider about the center cell, and this is the centered cell experimental and simulated results. These two have like the really good agreement also. So as the conclusion, what I can say is good agreement between the simulations and the experimental. However, there are kind of like the minor deviations also attributed, but it was happened due to the fixing issues of the heating elements during the experiments, as well as also there's kind of like the environmental temperatures also affect, and the environmental conditions also affect. And when consider about the temperature distribution in battery modules, it can be seen that they are depends on the cell special arrangement as well as the intercell distance, and results confirm that the 4x6 cubic structure is really better in terms of cooling capacity. However, 19 cells hexagonal arrangement was chosen because it has like the good space utilization, and because we are going to fix this one inside the automobile vehicle, so we have to consider about the space utilization as well. So that is the thing that's why we use 19 cells hexagonal arrangement. And also the simulation and experimental results indicate that the intercell distance is proportional to the cooling capacity of the module. And for the future work, I have to build up the composite case, which has the variable thermal conductivity, and how to identify the, now I am identifying the areas which are for the highly in the temperatures and the heat, and the required thermal conductivity of the composite case will be confirmed to the heat dissipation requirements, and also how to measure and validate the thermal behavior of the composite case finally. My project is funded from Lloyd's, and thank you very much. If you have any questions, please ask.
Thank you, Thamasha. Okay, so just have a quick look at the chat. So just waiting for those to come through. Okay, so, so whilst we're waiting, so just for my understanding, a couple of comments from your presentation. The first one was you did the validation for your single cell. And you say there's good agreement, but yes, you can see that there's a divergence in behavior. Your simulation seems to overestimate the response. So I was just wondering whether or not you've looked into or investigated that, because that's overestimation didn't seem to be present in the more complicated arrangement. So you look into that?
Yeah, the deviations happen because of the environmental factors, because, you know, in the simulation, there is no deviations, because in the simulation means like the perfect environment, but in the actual environment, there are kind of like the environmental temperature is changing and fluctuating, and also the convection heat transfer is also based, I mean, it's also varying in the actual temperature. So in order to avoid the fluctuations, I used kind of like the additional heat transfer coefficient also in my simulation. So, but still there's kind of like the deviations, but when I'm doing the module thing, I can negligible these things, because mostly they have like the almost good agreement between each other, because some of agreements, some of deviations I can't avoid, the unavoidable environmental fluctuations and the atmospheric temperatures. So that's the thing.
Okay. There's a question come through on the chat, and it reads, are there any other properties of the composite housing that you need to consider besides heat transfer?
Sorry?
Are there any other properties of the composite housing that you need to consider besides heat transfer?
Yes, of course. I have to consider about the weight of the composite, because this is how to be associated in the automobile. If this one, the composite became like the kind of like adding additional mass to the system, then again there is like the complication, because the existing systems, they have like they are adding some extra masses. So that is the thing that we need to avoid. So I have to especially consider about the mass of the composite, as well as the thermal conductivity, and also the structural ability of the structural integrity of the composite, because than the thermal conductivity of the composite.
Okay, thank you. So just one final question. So in terms of you've compared different packing arrangements, and you're comparing sort of 24 batteries versus your 19 hexagonal cell. How does the hexagonal cell translate to real world packing of batteries in an electric vehicle?
The hexagonal is into the real world means this one is considered as for the space utilization, because it's like, in the hexagonal arrangement means mostly the structural, it has mostly the structural stability when we consider about the hexagonal thing in the normal scenario. So that's why we use the hexagonal arrangement in the real world. That is the thing. And mostly they are okay with the hexagonal arrangement, because in terms of the space utilization, that's the thing. And we have to increase the power, because normally they have like the 24, but this is the 19, and how to increase the power of the each cell. But in terms of the space utilization, 19 cells hexagonal is really good.
Okay, excellent. All right, well, thank you very much for the questions. I think the one last quick question that just come through, and it says, in your heat transfer simulation, do you take account of both conduction and convection? And in the latter case, is it both forced and natural convection?
Everything I have considered, like the thermal conductivity as well as the heat transfer, the convection coefficient. But in order to simplify these things, I use the Biot number method, like the lumped capacitance. However, the thing is here, inside, when we consider about the airflow, this airflow has like the velocity, therefore the forced convection is used. And because the forced convection coefficient is used when simulation. And the other thing is for the sometimes they are using like the how to get the normal environmental parameters. In order to tackle with the normal environmental parameters, I use the free air convection as well. So both forced and free air convection are used in the simulations. So that's the thing.
Excellent. Okay, so please feel free to keep posting the questions to any of the speakers this morning. So we're just a few minutes over, but again, I'd just like to thank all of the speakers for their excellent presentations during this morning's composites and polymer session. And again, also thank you to the participants for posting their questions. So we're going to bring this session to a close now. We're off now for a lunch break, and the composites and polymer session will resume at 1 o'clock UK time. So please enjoy your lunch, stretch your legs, and we'll hopefully see you all soon. Bye-bye.
Brilliant. Thank you, everyone. And thank you, Kevin, for chairing a great session, and also to Bernadette for judging the session too. Obviously, feel free to stick around if you like. As you know, we will be here for the rest of the day. So thank you both for your time, and have a good afternoon.
You're welcome.
Hello, everybody. Welcome to this second session of the Composites and Polymers set of talks for the 2021 NSIRC Student Conference. So my name is Alan Taylor. I'm a Technology Fellow within the Polymers and Composites Technology Group within TWI, and it's my privilege to be the chair for this afternoon's session of, as I say, of the Composites and Polymers session. I'd like to thank Brunel Composites Centre and Teesside University for sponsoring this session. We have some very interesting talks given this morning, and we've got 4 extremely interesting talks lined up. So it's my pleasure to introduce to you the first of our speakers this afternoon. So welcome to Hamad Raheem, who is a 2nd year student at Cambridge University. So over to you, Hamad.
Thank you very much, Alan, for the introduction, and it's good to see you, of course. So I'm going to go ahead and share my screen. I assume my voice is clear, sound.
Wonderful.
Okay, so without any further ado, I'll get started. Let me just trying to move around the Zoom photos. Okay, so the title of the presentation is Evaluation of Polymer Aging Due to Gas Permeation Using Piezoelectric Micromachined Ultrasonic Transducers. Of course, all thanks to NIC, Non-Metallic Innovation Center, and NSIRC for funding this project. And let's get started. So I'm going to spend a minute or two talking about the motivation of this research and why actually this project adds value directly to the industry. So I come from a petroleum background as a petroleum engineer, and then I shifted gear to material science. And in the oil and gas industry, of course, stainless steel is a very important material, and it is known to be resilient for high temperature and pressure. It's the conduit for almost all fluids in the oil and gas industry, from subsurface to above ground, production facilities, all the surface facilities, the refineries. But the corrosion issue that faces the stainless steel is a costly one, not only because it has to replace the material every once in a while, depending on the corrosive environment that is subjected to, from 5 years to shortly 6 months in some occasions, but also the cost of shutting in production while changing this material and its heavy use and all of that. So thermoplastics, although they're presented as an alternative 30 years ago and deployed by Saudi Aramco and some European countries as well, provide perhaps a higher capex to start with, but then over the long run, because of the corrosion issue, they're claimed to be operatively less costly. So the intention of this project is to add value in terms of enhancing the material standardization that is that goes along with the polymers, and understanding how do they age and how do they respond to high temperatures and pressures. Of course, their operation envelope is very different to the stainless steel ones. They only operate around in the region of up to 90 degrees centigrade and 400 bars, let's say 500 bars, from my understanding. There could be some exceptions, but that's the overall operating envelope of it. So the project could be divided into two sub projects, in which the first part is to evaluate the signs of aging by exposing the specimens, the polymer specimens. And to note, the polymers that I'm talking about, they're of polyethylene grades, mostly high density polyethylene, and another one called the raised temperature polyethylene, which is a little bit different to the high density polyethylene in the chemical makeup. And so the first part is to induce age the specimens using continuous permeation methodology that is set up for weeks and under high pressure and temperature conditions. And the second part, where the PMUT, the piezoelectric microchip, comes in, is to serve as an early warning detection system for the aging. Now, we'll go into detail what the umbrella word aging means in the upcoming slides. And so it is to be a non-destructive methodology, an NDT, but is, of course, the project itself is supported and will be supplemented with other destructive tests, such as the DSC, the Raman spectroscopy, X-ray diffraction, and so on. So by polymer aging, it is a widely umbrella term that is used and can be called many different alterations that take place both mechanically and chemically to the polymer's makeup. And in short, one could put it down as the loss of performance, but that is also arguably and sometimes perhaps true and not true. So there are different types of aging. There could be thermal degradation, depletion of additives due to exposure to some plasticizers or thermal or pressure fatigues, cracks, which is one of the easy ones, the best, the tensors, the mechanical ones, which sometimes are caused by outside factors, which are very common in the oil and gas industry, since most of these pipelines are in vast lands and they're exposed to the wild, and so comes the weathering factor as well. Now, because the aging umbrella is a wide one should and could tackle this from different angles and different perspectives. Now, with the changing crystallinity could be a factor that could be monitored, for example, by the thicknesses of the lamellae, which are the stack of the polymer chains, using, for example, the diffraction calorimetry tests, crystal orientation using the X-ray diffraction, for example, microfracture networks. Another indication could it be by monitoring before and after aging using SEM, for example. Elastic constants, which is one of the ones that I'm focusing and working up together with percent crystallinity, as I will explain later on, can give good indications, as we see, because the Young's modulus and some elastic moduli change when the mechanical makeup or the chemical makeup of the polymer has changed. And of course, another indicator would be the content of additives that could be traced by, let's say, Raman spectroscopy, for example, or any other chemical tests. So the methodology for aging or artificially aging the polymers is with continuous permeation methodology, and that is with putting the sample discs, which are presented in here. I've got polyethylene, so raised temperature polyethylene at the left, and high density polyethylene sample with 2% UV light protection is added to it. That's why the black color. They're placed into this disc holder, a metallic disc holder, and a gas supply is inlet in here with high pressure, depending on the gas combination and the conditions of the pressure and temperature. And this is all in an oven, a thermocouple or an autoclave. And then the other side is where the permeated gas is collected. So for example, if we're pumping down CO2 as a plasticizer in high pressure and temperature, being it a supercritical fluid at this stage, above 70 bars, and so then a nitrogen supply comes in and takes the permeate at a constant rate to be detected by the GC, the gas chromatographer, and this mechanism allows one to calculate the transport coefficients that are with the polymer in terms of diffusion coefficient, permeation coefficient, and solubility, all very well established in the 70s. In the 70s, using Arrhenius plots such as one presented here. And then the second part is to understand how one would be able to test with the microchip the elastic moduli. Essentially, that is what we're trying to test, alterations in the elastic moduli, and that is by studying first the resonance of the polymer, and then once we have the resonance of the polymer for the specific disk, the resonance was determined to be around 0.5 megahertz, and then later the PMAT was designed such that the fluxural resonance of the polymer disk matches the fluxural resonance of the PMUT with the given thicknesses and dimensions. And as a result, what we would have is that since these resonances are matching, once the PMUT is actuated using a voltage source, and I would need to explain a little bit how this microchip works. And this microchip, a PMUT, is basically a piezoelectric layer sandwiched between two metallic layers, and this would give the effect of a capacitor. And once the one face of the capacitor is actuated with a voltage high enough, then the piezoelectric layer turns that electric energy to mechanical, and an ultrasonic chirp is sent away to the polymer. And then from there, depending on the resonance of the polymer, anything coming back would be accounted as an acoustic signature. Now, this could both serve as a receiver and a transmitter. One could put different configurations of PMUTs, for example, one in the top and another one in the bottom. Of course, here we're talking the medium being air. So these chirps are going back and forth through air. And then depending on the transmitter and the receiver, one could determine the elastic moduli through reverse calculation of the frequency waves. So here is a little schematic of how the PMUT would be placed. So the PMUT is going to be placed in here in a bonded to a circuit, and then the PMUT disk, the other side of this block, is going to be on a movable target, so that we have measurements at different distances and measurements at different times as well. Now, this setup is meant to be for air to start with, because it is a fairly new technique that the PMUT is being used alongside with solids. Usually the PMUTs are reported to be used, for example, in bioengineering, for example, in characterizing the sugar content in the blood, glucose content in the blood. So they were proven to work with liquids, but I think to my understanding, it is the first time is to be used alongside with solids. So the idea is we have the acoustic signatures for the virgin samples, the unaged samples, and then after a while for the aged samples, and see if there is any changes that could be detected by the changes in the elastic moduli. Now this, we haven't reached to that stage of our project yet, since these samples are still in the rig, and the microchips are manufactured and ready to be delivered from the USA by the end of the month. And so these results are pending. So the reason why I would focus on the Young's modulus and the elastic constant is that because one then could relate, for example, Young's modulus to the chemical makeup of the polymer. So, for example, one would be able to, for example, calculate the percent crystallinity and lamellar thickness from destructive tests such as the DSC, and then from the lamellar thickness, there are correlations. Correlations between crystallinity and elasticity that are reported for polyethylene, that one could reproduce these experiments and do the calculations and see if there is a link between crystallinity and the Young's modulus. Now,
1 minute, please, Hamad. 1 minute.
Right.
Thank you. 1 minute, please.
Okay.
So please continue. You just got 1 minute left, so.
Oh, okay. Oh, I see. Okay. So yeah, I'm going to wrap it up very soon. So one of the future goals is to talk about the try to, instead of putting it in air, we'll try to embed that inside, for example, the HDPE molding in the future, or the thermoplastic layers. But this is a lot of work to be done for that. So in terms of the results, we have very preliminary results, and that we have seen changes in the virgin samples, differences between the high density polyethylene and the raised temperature polyethylene. Although the change in densities are very, very subtle. Also acoustically, we've seen changes between the raised temperature polyethylene and high density polyethylene. Although their densities are very similar in their chemical makeup, but they are distinguishable at certain ranges of the ultrasonic spectrum. So in summary, so what we're trying to do is we've got permeation work to induce aging in the polymers, and then try to monitor these aging parameters using some non-destructive tests, for example, the MEMS technology, the PMOT, and some destructive tests such as the DSC and such. Of course, the significance of this contribution is big in terms of the oil and gas industry, because it will allow for the consideration of new NDT mechanisms in the oil and gas industry, and of course add value to the standardization procedures for polymers in general. So with that, I would like to open the floor for any questions, and if we run out of time, then we'll answer them in the comment box. Thanks, Helen, for reminding me.
No problems. Thank you very much, Hamad. Do you have any questions, please? Okay, we don't have anything in the chat box, and as we said, we're running a little tight on. So very quick question from me, Hamad, on the Bilbao spectroscopy graph that you showed very briefly. It looks as though there's a range of frequencies where you're getting quite a lot of separation between the samples. Can you just explain why in that particular frequency range you're seeing those differences?
Of course, it is in the initial stages, and it's very hard for me to predict exactly in what stages would these frequencies do differ. But we found that also using some destructive tests, that at very high frequencies, the additive, that is the 2% additive that is added in the high density polyethylene, perhaps would be the contributing reason why we see that difference in the high frequency only. However, in the low frequency, they're inseparable.
Splendid. Thank you very much.
Thank you.
Very much, Hamad. That's a very interesting talk. And again, any questions, please send them into the chat box, and we'll make sure we get a response to you.
And we'd be happy to answer. Yep. Thank you very much.
So, Hamad, if you would mind just screen now, that would be excellent. And let's move on to our second presentation of this afternoon's session. So again, it's my pleasure to introduce Malallah Al-Awati, who's a second-year NSIRC student at Birmingham University. So, Malallah, I will pass over to you.
Hello.
Hi, hello.
Hi. Yeah, can you hear me now?
We can hear you now, yes. So if you wouldn't mind going presentation mode, and then please start your presentation. Thank you.
All right, so my name is Mal, and today I'll be talking about my project, which focuses on powder hot isostatic pressing of titanium-based metal matrix composites for high wear resistance applications. And this is done with in collaboration with NSIRC and the University of Birmingham. So just quickly going over the presentation outline, the background will focus on titanium metal matrix composites for wear applications, and then the difference between in situ and ex situ processing, the aim of the study, and then we're moving on into materials and the experimental section, and moving then into the results and discussion, and finally with the conclusions. So just a quick background on titanium 6-4. It offers very high specific strength, and it's very light in weight. However, some of the drawbacks is that it has a low Young's modulus and it's not suitable for high temperature applications. And the major problem is like the poor wear resistance. And this is where like titanium metal composites come into play because they offer very high micro hardness and superior wear resistance. And they can also offer weight reductions. Some of the reported TMC titanium metal matrix composites applications is that it's been used in engine connecting rods, engine valves, and thin wall pipes. Some of the major challenges that happen with titanium metal matrix composites production is that there's a lot of challenges in dispersing the reinforcement into the matrix, and also challenges within the powder preparation routes because of the reactivity of titanium, and reduction in elongation and some mechanical properties. There's also a lot of difficulty in hipping canisters, and also the formation of brittle intermetallic phases. So the first table just basically shows some of the most common reinforcements used in the literature. And for example, we have like graphene, and the in situ formed phases you get is titanium carbides, and we have also the hipping temperature used in some of the mechanical properties associated with them. And in terms of in situ processing versus ex situ processing, so in situ processing, you have new compounds forming during hipping and consolidation. And in ex situ processing, no new compounds are formed. Some examples of starting additives for in situ processing is boron, for example, and graphene. And for ex situ processing, you have additives such as titanium carbide, for example, or titanium boride. And the main difference is that in situ processing, you get the change in morphology from in situ reactions. For example, the titanium diboride can react with titanium, and you can get titanium boride needles. And in ex situ processing, there is no change in size or morphology. The main advantage of in situ processing is superior interfacial bonding between the matrix and reinforcement, and also the enhanced tribological behavior compared to ex situ processing. Just quickly going over the aim of the study, it's to develop a suitable titanium metal matrix composite material which possesses a good balance between mechanical and tribological properties. So basically, a composite that isn't going to crack and has some ductility in it too. And the main objectives of this project is to develop advanced TMCs for high wear resistance applications via in situ reactions. And that's looking into different reinforcement types, for example, boron, graphene nanoplatelets, looking into the influence of reinforcement volume fraction and size, and also looking into process parameters such as the hipping temperature. And finally, assessing the hot isostatically pressed materials, microstructure, and then looking into the mechanical and tribological performance. Just quickly going over the experimental procedure, we get the as received powders, and we look into the powder morphology using an SEM. And then after that, we blend the titanium 6,4 matrix with the reinforcements using low energy ball milling. And so basically we mechanically alloy the composites. And after that, we produce the canisters, mild steel canisters, in which we fill the powders in, and then it goes through an outgassing procedure, and then it's basically crimped and moved into the hipping section of the procedure. And after that, we extract the materials for characterization and mechanical and tribological testing. In terms of the powder characterization, these are some of the as received powders. Picture A has titanium 6,4, the micrograph of titanium 6,4, and the powder size is 15 to 45 microns. And then micrograph B shows boron, which was as received as 1 micron. And then in diagram C, we can see the deagglomerated graphene nanoplatelets, which has been deagglomerated using ultrasonication with ethanol in it. And after that, the powders were mechanically alloyed via low energy ball milling. And below we can see the micrographs of the different blended powders. So in the first micrograph, we can see titanium-64 with 1 volume% graphene. And in the second one, titanium-64 with 2 volume% graphene. And then the third one with 1 volume% boron. And finally, we have titanium-64 with 1 volume% boron and 1 volume% graphene. And then we will look into the in situ reactions. So we also did some characterization works in terms of using Raman spectroscopy just to confirm that the as received powders was graphene and not graphite. And basically, because of like the distinctive bands and the Raman shifts, we can confirm that the powder was graphene. So here we have the XRD of the as-hipped titanium metal matrix composites, which were processed at a temperature of 1040 degrees for a dwell time of 3 hours and a pressure of 140 megapascals. And we can see below in the first XRD, titanium-64 with 1 volume% graphene, and the blue one is titanium-64 with 2 volume% graphene. So basically, we can see that the graphene has reacted with titanium-64, and we get like titanium carbide phase. And in the blue one, which has 2 volume% graphene, we have a higher retention of titanium carbide phase compared to the orange one because of the higher volume fraction of graphene. And in the second XRD scan, we have titanium-64 with 1 volume% graphene and boron on the top. And on the bottom, we have titanium-64 with 1 volume% boron. And we can see that we retained, in the first one, titanium boride and titanium carbide phases. And below, we had boron reacting with titanium-64 to form titanium boride. So here we have some SEM micrographs of the TMCs. So on the left side, we have them, as mentioned before, hipped at 1040 degrees. So here we basically, in image A, we have we can see some titanium carbides forming, and on B we have a higher volume fraction of titanium carbide because, as we mentioned, we have a higher reinforcement volume fraction of graphene. And below we have in micrograph C titanium-64 with 1 volume% boron, and we can see some fine titanium boride needles forming. And in the last image, micrograph D, we can see titanium-64 with 1 volume% boron and 1 volume% graphene, and we can see both titanium carbide and some titanium boride needles also. On the right-hand side, we wanted to look into the influence of hipping temperature on the in situ reaction of titanium metal matrix composites, keeping the volume fraction of graphene at 1%, so we can compare the different micrographs. In the first one, we did it at the hipping temperature of titanium, so below the beta transist temperature at 920 degrees. And you can see that there is a lot of porosities. There is an in situ reaction taking place, but it's incomplete. However, we have we can see some submicron or nanographene also present, which could be beneficial to the mechanical properties. And then the image in the middle was hipped at 1040, and you can see that we have a full reaction taking place, and there's no porosities and complete consolidation. And the last one at a super transist temperature of 1160, you can see that we have a full reaction, but we have also coarsening and agglomeration of titanium carbides.
1 minute left, please. 1 minute.
Oh, sorry. So just looking into some of wear typological properties that we've done some wear testing, and we can see that increasing the volume fraction of graphene, for example, improves the wear properties. And also, we did some Raman spectroscopy on the worn surfaces, and we can see that there is still some graphene present, which could explain why the wear rate, why there is less wear because of the lubricating factor of graphene. And just in conclusion, increasing the volume fraction of graphene increases the micro hardness due to the low transfer mechanism and more retention of titanium carbide phase. hipping at 11/16 shows full consolidation. However, that results in green growth, while hipping at 9/20 shows a lack of consolidation and no in-situ reaction. And hipping at 10/40 resulted in retention of titanium carbide with some unreacted graphene, which helps in the tribological performance. And finally, increasing the volume percent of graphene reduces the coefficient of friction due to an increase in micro hardness and an increase in graphene content. Thank you for listening. Any questions?
Thank you very much, Mal. That was a very interesting presentation. So we do have time for questions. So if anybody in the audience would like to ask one, please do so via the chat box. Okay, so quick question from me, Mal. It was very interesting what you're saying in terms of the interfacial characteristics that you're looking for. I was just curious about the influence of time on the processing conditions. Is that one of the areas that you're going to be looking into, or are you maintaining that at maintaining the processing at a constant time? I'm just wondering about the influence of the growth of the interfacial regions.
So basically, in this work, we just looked into the influence of the hipping temperature, not the dwell time. But in previous work, I've looked at changing the time, and that did affect basically the amount of in-situ reactions taking place. However, that wasn't presented in this work, but yes.
But there's an influence of both time and temperature, which I guess.
Yes, but the main driver is temperature in hipping. Yeah.
Thank you very much for your clear answer. Thank you.
No worries.
Thanks, Mal, for your presentation. So I'd like to move on to the, if you wouldn't mind, stop sharing your screen, and we'll.
Yes, sure.
So our next presenter. So. And it's my pleasure to present Burak to the audience. Burak is a second-year student at Brunel University.
Hi, good afternoon. Can you hear me?
Yep, very clearly. Thank you. So if you could go to presentation mode, that would be splendid. Thank you.
I think I can prevent this.
Okay.
Hi, I'm Burak Sakarya. I'm in the second year of my PhD project. I'm a doctoral researcher by Brunel University London. This project is funded by the World Registries Foundation. So the presentation consists of 5 main sections. First is the introduction to composite pressure vessels, which I'm going to describe and demonstrate what type of structures is the focus of interest in this project, and then aim and objectives and the impact factor of research. And one of the completed objectives will be demonstrated as develop analytical tool, and an introduction to the design concept of liquid fabric. So composite pressure vessels are manufactured by the fiber reinforced composite, and fiber reinforced composite has a significant role in the industry for advanced applications because of their high strength to weight ratio and crash work abilities, corrosion resistance, and so on and so forth. The critical failure in these structures in composite pressure vessels is the burst pressure. So there is a methodology which there is a method which known as liquid fabric, and liquid fabric is basically provide a visual inspection for the leakage before the catastrophic failure. So the preventative action can be taken to prevent the catastrophic failure. And there are analytical and numerical studies to estimate the liquid fabric within the structure. So in this project, I am working on the development of liquid fabric concept. And the aim of the project is the development and proof of conceptual design, enabling inherent liquid fabric capability in composite pressure vessels. The objectives are the development of analytical solution enabling rapid investigation of potential fail-safe patterns, development and design composite for liquid fabric by using finite element method, an artificial damage approach, proof of concept by performing validation of the best scenario coming from the numerical solutions. So the impact of this research is there is no available method to evaluate the leak before break capability of the composite pressure vessels. So in this project, from the design of the structure to the leak before break concept, a comprehensive design methodology by using numerical and analytical tools is aimed, and it will be performed by the finite element tools. And one of the completed objectives is to develop analytical tool. This is a data structure-based algorithm prepared by using MATLAB commercial software, and you see a short description of the analytical tool algorithm. So basically, it starts from the calculation of the stiffness and complex matrix of each layer, and then by control volume approach, equivalent global and stiffness matrices are calculated, and applying layer equations and the transformations of the between the principal axis and global axis system. The failure criteria as first apply failure is used for the burst estimation. The developed analytical tool is not directly related to the leak before break concept, but it is necessary to ensure that the structure has enough strength so that the premature failure can be prevented to enable leakage. So there are two case studies that used to evaluate the capability of the analytical tool. One of them is a thick pressure vessel, which you see in here is a part of the structure here, and this is validated by the results in literature, and also a finite element model by using shell elements are prepared, and appropriate boundary conditions and a shell edge load to represent the structural response of the composite pressure vessel are applied. The results has good correlation with the literature. The available result in the literature, which show with dotted lines in here, and the developed finite element model. The strain in the fiber direction was accurate, and the 2-to-1 hooked arterial stress ratio was observed. The second case was the thin pressure vessel model, differently from the previous case study. In this model, the carbon fiber reinforced epoxy material is used, and this model is prepared with the end cap to represent the structural response. So it was a necessary approach to obtain the accurate structural response. And the geometry of the structure and static sectors are described in here. So the strain results in on-axis and off-axis direction, which means fiber and transverse in plane direction, and the axial and hoop strain direction were consistent between the FAM case. And the energy balance also checked with the hourglassing phenomena, and it found negligible. It was consistent with was as expected regarding the accuracy of the finite element model. And the burst pressure has a good correlation with the prepared FAM model, and the hooked axial stress ratio was as expected in 2-to-1 hooked axial stress ratio. So the conclusion, accurate structural response and material response achieved, and the applicability of the analytical tool was found. It is applicable for thin and thick pressure vessel and different type of composite pressure vessels, which are type 2, 3, 4, and 5. And the first apply estimation used to evaluate the burst phenomena based on the maximum fiber tensile stress under linear elastic material response. And the second part I'm going to mention in this presentation is just introduction of the current work. Currently, I'm working on the design concept for leak before break, and This is prepared by a model. Again, the end caps are just used as a necessary thing to represent the structural response. And in here, the focus on interest is a type 5 pressure, composite pressure vessel, which means there is no liner in the structure. So the aim is to obtain the controllable crack roll and no drastic compensation of the strength. So to achieve this, Abacus software available commercial to for one element somewhere is used with mesoscale at mesoscale level. And when I say mesoscale level, it means the stress and strain calculations can be performed for each ply, and fiber and matrix constitute are not separately modeled. So in here, the aim is observing the through the thickness matrix damage in the floor inherited zone. We perform my material degradation, and when through the thickness matrix damage achieved, the pressurization of the structure can be performed to prevent catastrophic failure. So the leak before break concept will be achieved. And depending on the time of this project, small scale work also might be applied to provide a solution at the small scale rather than the vessel scale. And to separate both matrix and fiber damage mechanism within the structure to develop my leak before break concept, the progressive damage and failure model for fiber reinforced composite materials available in Abacus is used. And here you see one of the results that applied for to prove that the material response is accurate regarding to applied inherited material properties. The stress strain curve in fiber direction and in the transverse direction, which means basically principal materials direction, they were as expected, which was a good correlation with the material parameters. So that's all from my side. Thank you very much for your attention, and thanks for Logistics Foundation for sponsorship, and thanks NSIRC and my principal supervisors and academic supervisors and industry supervisors help through this project. Thank you very much.
Thank you very much, Burak. Very interesting talk. So I'd just like to, and thank you very much for being bang on time. So that's excellent. I'd just like to open to all of the audience and ask for any questions. So if there are any questions, please, if you could post them in the chat box, let us know. But while we're waiting for any questions, first quick question from me, if I may. Looks like a very interesting tool that you're developing there. Can it be used and adopted for different floor sizes or different floor geometries?
It can be used. But it's kind of case-by-case study, because I'm using a finite element approach in here. The application of the flow and the solver of the model, the mesh refinement should be implemented accurately, so it can be done. In here, this characterometer, for example, taken from a BS standard, there was, I think it was BS 12295, which is about the composite pressure vessels in composite pressure vessels for transportation purposes. And this characterometry is applied regarding to flow cylindrical test definitions in that standard. But the other type of material flows can be applicable, of course. It's just the material degradation level should be applicable regarding to what we are doing, whether it's fiber damage or matrix damage.
Splendid. Thank you very much for your answer.
Thank you.
Okay, well, we have a couple of questions coming up, so we'll take one of these. I'll take the last one to come in, and then if we reply to the others offline. So we've got a question here from Ahmed. Have you demonstrated the maximum allowable stress of the vessel before rupture?
For design composite for leak before break, I mean, I did, but it was just, it's not represented in this presentation because it's just a recent result. But regarding to the develop analytical tool, yes. So basically, I consider the fiber tensile failure in here, and in here, burst estimation for undamaged structure happened around 59.7 megapascal. So it achieved to observing the tensile, at which internal pressure that fiber tensile failure achieved in the structure.
Thank you very much. Well, we do have some other questions, but if we could capture those and then respond to those offline, that would be splendid.
Sure, no problem. Thank you very much.
Right, many thanks for your presentation.
Thank you.
Might stop sharing the screen, and we'll move on to the final presentation in this session. So again, I'm delighted to be able to introduce to everybody Maciej Gierulski, who's a second-year PhD student at the University of Sheffield.
Good afternoon.
Okay, over to you.
Yep, I will share my screen. Just let me start the presentation. Now, beginning. Yep, can you see the screen?
Perfect.
Good. So, welcome everyone. My name is Maciej Gierulski. I'm a PhD student at University of Sheffield. I'm going to talk about my project, electrofusion couplers for thermoplastic composite pipes. So to give a quick background, oil companies are looking to replace metallic pipelines, which are currently dominant for oil and gas transport, because steel pipelines and steel connectors are prone to corrosion, which can cause leaks, obviously. And this all means that regular maintenance is required on these pipes. So the aim of the project is to design a non-metallic connector using also non-metallic electrofusion welding technology for polyethylene composite pipes. The objectives include investigating the current state of the art in thermoplastic pipes and thermoplastic composite pipes and electrofusion welding, building a finite element model of the joint, and then testing electrofusion couplers available in the market, and finally designing a dedicated coupler for composite pipes. The target conditions we are looking at are 100 bar internal pressure and 65 to 80 degrees C operating temperature. So thermoplastic pipes are a very common solution in gas, water, and sewage distribution system installed nowadays, because they are cheap to produce, easy to install, and quite reliable. Their flexibility, the mechanical property, allows them to even endure earthquakes, as it happened in Japan in 1995, when the metallic pipelines required extensive repairs afterwards. Polyethylene pipes were intact. They are also chemically resistant, which means they can function for over half a century without maintenance. They are, though, limited in their pressure and temperature capacities, but this problem can partially be solved by reinforcing them. And they can be reinforced by any material like glass fiber, carbon fiber, aramid fiber, or even metals. This means they can now take higher pressures, but still keep their flexibility and do not corrode. So they are very good competition to steel pipelines. The picture you can see here shows what a thermoplastic composite pipe consists of. The inner layer contains the fluid, the reinforcement provides the strength, and the outer cover shields the other two from the environment. All three layers are welded together. This project utilizes glass fiber reinforced polyethylene. This is a novel material and little data is available on it. Some reinforced thermoplastic pipes are already in use in oil and gas industry, but they still use metallic connectors. And this is what we want to change. There are non-metallic joints for thermoplastic pipes, but they have not been widely applied to composite pipes. Electrofusion joints are a major and common technology for connecting thermoplastic pipes, and they offer better performance than mechanical joints in terms of strength and corrosion resistance. I'll explain how this process works. First, we clean the two pipes so that their surfaces are completely clean from any contamination. We slide them into the socket. Then current is applied to the wiring you can see in the drawing. The plastic in the fusion zone melts, then cools down, mixes, cools down, and forms a weld. The cold zones visible here are there to contain the molten material inside and generate pressure. And melt pressure is one of the main three factors that define the electrofusion welding process. The other two are peak temperature and heating time. Here you can see a graph of a typical process that can be divided into three phases. First, in the incubation phase, the plastic is heated but doesn't yet melt. It only melts in the second phase, and because of this, the pressure rises quickly. Finally, in the cooling phase, when heating is stopped, the pressure slowly decreases and the weld is formed. To influence these three factors, the engineer might change the heating time, the layout of the wiring and cold zones, the size of the clearance between the pipe and the coupler, and also choose a different material grade for the fitting. As I said previously, electrofusion joints can function for half a century or more, but they can also fail prematurely, especially if they are not made correctly. Here in the figure, we see four typical failure modes. They all correspond to different loading modes, so they happen in different situations. Number 1 and 2 happen when the weld is not made correctly. For example, when it is contaminated, gets underheated or overheated. Modes 3 and 4 happen in correctly made joints, which are subjected to excessive stresses. Number 3 happens when the pressure is too high and a crack forms in the inner cold zone notch and grows through the fitting wall. And number 4 happens when the axial load on the pipe is too high. In order to design a successful coupler, we need to know how it will respond to these two important loads. To get this knowledge from a range of tests that are available for quality control of electrofusion joints, we chose two. The whole pipe tensile test that's visible in the figure, where we basically pull the pipe out of the joint, and the hydrostatic pressure test, where we apply pressure. Both of them will be done physically and finite element modeled. And when done physically, they will be strain gauged, so I can extract the strains from the test and use these values to verify the finite element model. So the model can be then used to design the dedicated coupler. So a little bit about the model. It is done in Abaqus using solid element approach. The element size is 6 millimeters because this is the size of the strain gauge that we are going to apply. And it's also a compromise between the use of computing power and precision. I use the actual coupler geometry and model both the joint in polyethylene pipes, standard polyethylene pipes, and composite pipes, and compare their behavior. And as I said, the model will be validated with strain gauges and also digital image correlation data. So in order to have a faithful finite element model, we need good material data. Normally, in case of most composites, I would go to a database like Agate and get my data from there. But unfortunately, this material is novel and it's not present in most databases. So the natural solution in this case would be to do the three tests that you can see to the right, where you essentially pull a flat plate of a composite in three directions to get both Young's moduli and shear modulus. However, no, it's not possible here because we don't have a flat plate of the material. We only have a pipe. So it requires a non-standard testing procedure, and to perform it, I chose three tests: ISO 527, which is a standard tensile test to get the tensile modulus and strength in the axial direction; ASTM D20-90, slightly modified to get the hoop properties; and the Yossi-Pescu shear test to get the shear properties. I model all the 3 tests also to make sure that the curvature of the sample doesn't influence the result. Before I've done the test, I have to use values calculated using classical laminate theory. And the results of the simulations are promising. When the reinforcement is introduced, it takes most of the load off the coupler. And you can see here to the right, both drawings are in the same color scale, and blue means less stress. So you can clearly see the reinforced pipe joint is less stressed. And the stress concentration stays in the cold zone notch. This doesn't change, which is a good news, because it means the design process will be easier. And also, I'm quite happy that the stress value goes down below the yield strength of plastic, of polyethylene. In order to perform any of the trials, the pipes need to be not perfectly, but at least kind of straight and round. And the pipes that we were supplied by our provider are quite bent and oval because they were transported in spools. So if they are not round, then it will be very difficult to insert them into the coupler and also to produce specimens. And if they are curved, the strain gauge readings will be affected. They won't be symmetric on both sides, and it will be difficult to verify the model with them. To solve this problem, a straightening jig was built and a procedure was devised in which I put the pipe segment on the jig, insert it into a weathering machine, and leave it at 80 degrees C for several hours. And this idea was successful. The angle, as you can see, I was able to decrease the curvature to below 1 degree over a 60 centimeter segment. And the ovality goes down from up to 5% to below 1%, which is already enough, small enough for the pipes to be welded. The next steps in the project include getting myself trained in using all the testing equipment that we have to do for all the experiments, manufacturing the samples and performing specimen tests to get the material data, obviously developing the final element model, and finally verifying the model against the full tests. That's all. Thank you for your attention, and I'll be happy to hear your questions.
Well, thank you very much, Maciej. That was a very interesting presentation. So we do have one question. So question from Suleiman, who's asked, is the design coupler made of a monolayer composite matrix or a multi-layer structure with composite matrix as mid layer?
Yeah, so at this stage, we cannot, well, the market available couplers are just the resin, just the polyethylene. But we guess we will have to use composite couplers because the pressures that we are looking at are very high. It's 10 megapascals compared to 2 megapascals that I used in the simulations. So the desired coupler will definitely be reinforced.
Splendid. So we've got a second question come up here, which is how do electrofusion joints compare to swaging and interlocking techniques for joining TCPs?
Swaging and interlocking. So the main problem is that these joints will be metallic and they will corrode. That's the main problem. And also an electrofusion joint is much simpler. It basically only requires, it is done by one supplier, and sometimes you need a different supplier for each part of a mechanical joint, because you have seals, bolts, nuts, and etc. And you also need you need to do maintenance on metallic joints, on mechanical joints, as you said. And as far as the industry experience says, electrofusion joints are maintenance-free completely.
Splendid, thank you very much. With no further questions, I'd just like to thank all four of our presenters in this afternoon's session of the Composites and Polymers program. So thank you to everybody. I believe we've now got a break for 15 minutes before the next session starts. So we'll close for the next 15 minutes. So take the opportunity to get yourself a cup of tea or a drink of water or whatever you have, and we'll see you all back in 15 minutes. Okay.
Thank you.
Okay, good afternoon. Welcome to the last session of day one. This is the Joining Technologies session, which has been kindly sponsored by TWI Certification Limited and Coventry University. My name is Jonathan Martin. I'm a technology manager working at TWI. So I do encourage you to please join in and participate by submitting your questions by clicking on the question and answer icon. In this session, we have, are you okay, Mohammed? We have 3 presentations in this session, 2 are live and 1 pre-recorded. So can I introduce the first presenter, Mohammad Khairy, who is the 3rd-year student with Brunel University. His presentation is on the effect of partial pressure of hydrogen on vacuum brazing of 316L stainless steel. So over to you, Mohammed.
My name is Mohammad Khairy. I'm 3rd year student, Brunel University, London. My research is sponsored by TWI. It's about vacuum brazing of 316 stainless steel. So the background of the project, brazing is a thermal joining process, just like welding. We use heat and filament to join the parts. The most important thing about brazing is you need to have perfect wetting so you can have a good capillary action to fill the gap. The problem with 316L, it is corrosion resistant, and it is mainly because of the stable oxide film. But this oxide film prevents wetting. So in case of brazing, we either remove it by doing the brazing process at very high temperature, relatively very high temperature, above 1000 degrees C, or we need to do some surface treatment like nickel plating. So what we aim to introduce hydrogen as reducing agent, and we believe that we might be able to reduce this oxide film without the need to go to higher temperature or using this surface treatment measures. So the oxide film on the 316 stainless steel, it's a bit complicated and it depends on the treatment process. So if it grows naturally, it is different than the one that grows through passivation chemical treatment. So, but the native oxide film that grows naturally, it's mainly composed of basically 2 layers. The top one is rich in iron oxide and the bottom one is rich in chromium oxide. I'm mainly concerned, I'm focusing in this project on this chromium oxide because we do the brazing at above 600 degrees C, and above 600 degrees C, if any oxide remains, it will definitely be chromium oxide because it's the most stable one. And this is a simple schematic to show how this oxide layer looks like. And as we increase the temperature, as we heat in vacuum, the less stable oxide, the iron oxides, and molybdenum oxide, and so on, it disappears and it gets replaced by chromium oxide. And at certain temperature, even the chromium oxide can be removed. So this photo explains why this oxide layer is problematic. As you can see here, this is 316L plate. And this is silver copper eutectic filler metal. As you can see, there is no wetting at all. It's just forming a ball shape. So how can we achieve this wetting? It's either by totally remove this oxide film, total reduction. And in this case, as we can see, we can call this good wetting for brazing with a contact angle almost less than 20 degrees, or it can be partially removed or get weakened and cracked, and the filler metal penetrates it and lifts it off. Both causes are reported in literature. So in any ways, we have to remove this oxide film. And the problem of this oxide film, even if we remove it mechanically prior to introducing the sample into the furnace, it will grow as we heat it up to the brazing temperature at temperature below 500 degrees. So you have to have any means to remove it while you are brazing. The theory behind the removal of oxide film is simply that any oxidation reaction can be reversed by controlling the temperature and the amount of oxygen within the atmosphere. So this is called Gibbs energy of the reaction. If it is zero, it means that we reach equilibrium condition. If it is negative, it means that the oxide film is stable. And if it is positive, it means that the oxide film is not stable anymore and can be removed. So as we can see from this equation, this you can consider it as constant. You can get it from thermodynamic data from handbook, and you can extrapolate it with some calculation to a range of temperature. So you are merely concerned about the temperature and the partial pressure of oxygen. And this is how the so-called Ellingham diagram is plotted. And it is very useful, and it is used to extract metals from its ores. So as you can see here, as you go down, these oxides are more stable. And it tells you that the elements which has more stable oxide film can be used as reducing agent for the one with less oxide film. As an example here, iron ore is extracted through with carbon through a simple process. As you can see here, this reaction above 600 degrees has more negative Gibbs energy. So that's why we can extract iron from iron oxide by mixing it with carbon and heating it at above certain temperature. And we can see here clearly that the chromium oxide is the most stable one within the oxide within the 316L. That's why all the calculation is based on the chromium oxide. Ideally, we should do this experiment in situ. I mean, while we heat the sample itself at such temperature above 600 degrees, but it is complicated. Firstly, it's high temperature. Secondly, we are using hydrogen, so there is no such equipment to do it in situ. So we will do it ex situ. And what I mean by ex situ, that we will conduct the wetting trials, and we will test the solidified samples to assess the contact angle and area and so on. So basically, it's simple qualitative assessment, contact angle and area. Then when we reach the optimum condition in terms of temperature, pressure, holding time, we'll do further heat treatment to analyze the oxide film after and before heat treatment, and we'll do actual brazing joint. I'm still at this stage, haven't moved from this stage yet. I've done almost 19 furnace runs, and I've just started getting some positive results. So how hydrogen is controlling the oxide, the oxygen within the furnace? This is the oxidation. This is the water formation reaction. Simple one, hydrogen and oxygen gives water. So this tells you clearly that when you control you can control the amount of the oxygen within the atmosphere by controlling the ratio of water content to the hydrogen. So in our case, we have fixed percentage of hydrogen. So we aim to have as dry as possible gas to be used within the furnace. I've done this thermodynamic modeling, assuming that the furnace that we are using, when we introduce the gas, it reached 0.5 millibar. So at this 0.5 millibar, I'm using just 5% hydrogen because of safety reason. I can't use above 7% because it is flammable above 7%. And this percentage is controlled by using ready mixture. It's either hydrogen in nitrogen or hydrogen in argon. So it is just 5%. Based on this information and the available data regarding the formation of chromium oxide, I've done this thermodynamic modeling. I've done it for a range of mixtures, which is commercially available in the market. So we can see here, if we use such mixture with water content up to 1.2 part per million, we should be able to remove the oxide film at temperature above 850, which I'm conducting my trials at from 850 to 1000 degrees. So this tells it should be fine. This is a typical experimental setup. This is the vacuum furnace we use. The lining is made of graphite and the heating elements are made of graphite as well. The filler metal I use silver copper eutectic because I need, because it is not reactive. So if we manage to achieve any wetting, it should be due to the reaction between the furnace atmosphere and the stainless steel itself, rather than the reaction between the filler metal and the stainless steel. So it is simply disc-shaped, the same volume, so we can even measure the area. And this is a typical brazing cycle. We pump it down to 10 to minus 5 millibar, hold it for 1 hour just to remove as much gases as possible. And then introduce the gas up to 0.5 millibar, hold it for 1 hour, then raise it to the brazing temperature, 30 minutes, cool it down. So for the preliminary results I've got so far, I haven't got what I was expecting with the first mixture I used. This is, I've got a contact angle of 60, and what reported in literature for high vacuum and proper brazing, it should be below 30 degrees. And this result is even worse than what I've got with vacuum. So I've tried to rule out the possibility of why we are getting these bad results, although the first calculation showed that it should be good results. One of them, the sample cleanliness, because I tried to use the simple procedures that used in industry, just wipe it with acetone or ultrasonic, cleaning in ultrasonic bath with acetone. I will try to use a different method, even mechanical cleaning. The second possibility is because of the graphite lining and heating elements, it emits carbon dioxide, carbon monoxide, and water as well. So carbon monoxide shouldn't be a problem, but the water should be a problem. I started with the third one, which is the water content of the gas mixture. We changed to a newer gas mixture, the best one available at the market in terms of the water content. And fortunately, last week I started to get some promising results, but I'm not presenting it here because I'm still analyzing. But from the first view, we are getting some better results. For the future plan, using the dryer gas, the best available in the market, and we are getting some better results now. The depth profiling analysis and depth diffusible hydrogen measurements, we will do it after we obtain the optimum parameters in terms of temperature, holding time, and so on. Thank you for your time, and if you have any questions.
Thank you, Mohammad. That's a very interesting presentation, very clear. Let's see if we do have any questions. I don't think there's any in the Q&A or the chat. So while we're waiting, I can see your main aim of your project was to reduce the processing temperature, and I think that was to improve the tensile properties. Can you sort of quantify what, are the temperatures for normal vacuum brazing to the temperatures that you're trying to operate, what that difference will be in terms of the effect on tensile properties?
Yeah, actually, it is brazed above 1000 degrees, actually above around 1200 degrees, 1100 degrees, this range. It's currently brazed at this range using nickel filler. Or it can be done lower, but with nickel plating. So in terms of the effect on the tensile properties, according to the literature and according to some grain grain size measurements that I've already done, it should be fine up to 870 degrees C. But above that, it really starts to affect the grain size. In terms of effect on the tensile properties, it could be mitigated by changing the design of the joint itself, including the surface area and so on. So it is not a very big deal, but the need for special treatment, nickel plating and so on, this is the main issue, and we are trying to assess whether we can actually use a dirty joint, dirty seal, without even being worried about doing this pre-cleaning process and so on.
So you're getting more promising results now. So do you think?
Yeah. With the latest mixture I used, it is promising. I've just got some results last week. I couldn't include it here in the presentation because
do you think it is the water content and that is your main issue?
Yeah. So last week with the new guys, we started to get some promising results.
Good. Okay, I don't think we have. Okay, we do have one question that's come in. Do you have an idea how better brazing is compared to other joining processes?
Yeah, actually, it's not a matter of being better or not, but sometimes you are forced to use it. For example, when you have multiple joints, one part with multiple joints, the brazing is the economical choice. Sometimes you don't have even choice. Very thin parts, not accessible with conventional joining processes and so on. So it has some applications that you can only do it with brazing, or economically it should be done by brazing. Especially for mass production and multiple joints that you can produce just one shot. And in terms of material, because I'm here speaking about stainless steel, in terms of materials, there are some type of materials you can join with conventional welding. Brazing is the only possible process to be used.
Okay, Mohammad, thank you very much for your presentation. I think we need to move on now. So if you could stop sharing your screen.
Thank you.
The presenter is Tianmiao Li, who's a third-year student at Loughborough University. And the presentation is on cold atmospheric plasma treatment to enhance adhesive bonding. Do we have Tianmiao? Oh, good.
Hello everyone. Can you hear me? All right. I'm Tianmiao. My topic is cold atmospheric plasma treatment to enhance adhesive bonding. Here's the agenda of my presentation. Firstly, I'll introduce some background of my project and the project aim, and also the plasma generator I used for this project. And then I will show you some results of my work. And finally, I'll make a summary and introduce some future work. So first of all, what is a plasma? You'll hear it as the fourth state of matter. We are quite familiar with the first three states of them. They are solid, liquid, and gas. But what will happen after a gas? When we heat up a gas, the atoms in the gas are going to move faster. On the other hand, inside an atom, the electron is going to get some energy as well and start vibrating. Eventually, the electron is going to escape its orbit. And when that happens, we get our plasma. So in the plasma, the particles are charged, but the plasma overall is neutral. And like in a gas, the particles are moving around independently, but different from a gas, the plasma can conduct electricity. So what can the plasma do on our surface treatment? Physically, it can remove contaminants and clean the surface at a micro level. And chemically, it can increase surface free energy, activate the surface by introducing functional groups to achieve better surface properties. Why we use a plasma? Among the various methods of surface treatment, plasma is a highly respected method because it is able to be a contactless, dry, fast, safe, low energy cost, and clean process. The most unique advantage of our plasma is that it can be used for a large range of materials, from plastics to metals, from textiles to electronic components. And these advantages are highly in line with industrial preferences. The aim of this project is firstly to determine the potential of cold atmospheric plasma treatment on enhancing adhesive bonding, and then to understand the science behind the enhancement. The plasma generator I used in this project is a microwave plasma system. On the left here, it is the real nozzle I used. To generate a plasma, high frequency signal is applied to the antenna mounted inside the metal cavity, and it is one of the electrodes. The other one is the wall of the cavity. The antenna is used to concentrate the microwave energy. So the microwave will be caught and concentrated at the tip of the antenna, and sufficient energy will be transmitted to the gas to generate a plasma. With the gas flow here, the plasma will be spread out from the nozzle, and in this way we can use the plasma to treat a surface. For my experimental work, the first part is the plasma treatment of a glass fiber reinforced polyethylene. It is a thin sheet material containing 62% of continuous glass fiber. And the adhesive I used in this part is Erudite 2021, which is a methacrylate adhesive. The variables in this part were microwave power and plasma dwell time. Pure argon with 5 liter per minute flow rate and 5 millimeter nozzle to surface distance were fixed throughout the experiment. Lab shear is a very straightforward test to study the mechanical properties of a material. In this part, I used a sandwich structure joint structure. From this picture, we can see the failure mode changed after plasma treatment. For the IPA cleaned one, it is a pure adhesive failure. And most of the plasma treated ones, they showed a combination of multiple failure modes, including adhesive failure, cohesive failure of the composite, and cohesive failure of the adhesive. For the strength of the lab shear joints, the red line represents the IPA cleaned batch. and all the plasma treatment batches showed an increased bond strength. In general, high power and longer dwell time could result in a better bond strength. But for 30 watts microwave ignited plasma, dwell time over 1 second didn't cause an obvious increase in bond strength. One reason for the plateau here could be the heat from the plasma. The red line here is 130 degrees Celsius, which is also the melting point of HDPE. Over 2 seconds of dwell time, the 30 watts microwave ignited plasma could melt the surface. When it cooled down again, the sample surface became wrinkled. So we can speculate that the melting of the surface is undesirable. Now let's come back to the surface. How does a plasma change the surface properties? Contact angle test was conducted to measure the surface free energy, which is reflecting the wettability of the surface. In general, the surface free energy showed a similar trend as the bond strength. Long dwell time and high power could lead to a high surface free energy, but it may only reflect the properties of the very top layer of the surface. With respect to 30 watts microwave ignited plasma, for long dwell time, surface free energy could not give an accurate prediction to the bond strength, because the performance of an adhesive bonding is also related to the bulk property of the material. So what did the plasma change from the surface? To find that, FTIR was used to analyze the surface groups before and after treatment. The overall view of the spectra shows that the difference between H spectrum is around 1700 wave numbers. So if we zoom in this area here, there are two peaks. One about 1730 represents the carbonyl groups. The other about 1630 wave number represents the alkene groups. The intensity of carbonyl peaks increases with the increase of dwell time. It indicated that more carbonyl could be introduced onto the surface when the plasma is applied for a longer time. And when the plasma dwell time is over 5 seconds, we can see the alkene peak appeared. So it indicated that some polymer chains of HDPE were broken by the plasma. Now let's go through the key points of my glass PE work. In general, high microwave power or long dwell time could result in a high bond strength. The failure mode could be changed as well. And when using a 30 watts microwave ignited plasma, we should pay attention to its working temperature to avoid melting or over-treatment of the sample. The mechanism of the plasma treatment could be introducing carbonyl groups onto the surface. 30 watts microwave ignited plasma may break the polymer chains. So the other part of my project is the plasma treatment of aluminum alloy 2024 in T3 temper. And adhesive used here is Redex 319. It is a high-strength epoxy film adhesive, and it is specially designed for aluminum to aluminum joints. The variables in this part were gases combination and the dwell time as well. 30-watt microwave power and 5mm nozzle to surface distance were fixed throughout the experiment.
Yeah, well, probably another 1 or 2 minutes.
Okay.
Would you end? Yeah.
So let's just go to the key points. The plasma of argon and air in the ratio of 7.8 and 0.2 liter per minute was nearly comparable to chemical etching, and the dwell time did not significantly affect the bond strength. Appropriate dwell time improved the variability of the treatment. An enhancement mechanism might be introducing some polar groups to the surface. So far, we can get to conclusion that cold plasma with appropriate parameter is able to enhance the adhesive bonding of glass PE and also aluminum alloy 2024. For glass PE, we should pay attention to its working temperature to avoid melting or overtreatment. And for aluminum alloy, the selection of gas combination is important. In future, I'll conduct some SEM and XPS analysis for further studying of the surface changes by plasma. For the aluminum alloy, I'll try some other variables, such as different flow rate. At last, I would like to thank my supervisors and my colleagues. They helped me a lot. And also, I would like to thank the sponsors, NSIRC, TWI, and Loughborough University. Thank you for your attention.
Okay, thank you very much for your presentation. Again, very interesting. Let's see if we have any questions. So I think because we've run over, we won't have much time, but I believe this is sort of an aerospace type application.
Yes.
A lot of your tests, or your tests seem, obviously you've got the shear test. Have you considered looking at any dynamic testing, and what do you think the performance would be on the dynamic loading?
Mm-hmm.
How do you think the performance will be of these joints under dynamic loading? I say most of your tests have been static testing. Are you going to consider dynamic loading?
You mean fatigue test?
Yes, but yeah, like fatigue testing. Yeah.
It could be a future work, or maybe for myself or the next student, because I'm already third-year student.
Yes, it's still quite a long to. Let's see if there's any.
But I'm going to do a wedge test for the aluminum to see the aging resistance.
Yeah, yeah.
Yes.
So your shear strength was not quite as good as the acid etching process.
It is chromic acid etching.
Mm-hmm. So it is slightly below the strength you're obtaining. Is slightly below that obtained.
Yes, for Redox 319, because the adhesive is quite strong, and the result of the plasma treatment is quite good. It's nearly comparable to the chemical etching one, but I will try another adhesive to see if it is really comparable to the chemical etching.
Very, very good. I think we'll have to leave it there, but thank you very much for your.
Thank you so much
for your presentation. If there are any questions, please send them through. So the last presenter today is Michael Dodge, who's the principal project leader at TDRI. He works in the materials performance and characteristics section. He'll present on hydrogen embrittlement of high strength precipitation hardenable nickel alloys. Michael's presentation is pre-recorded. So perhaps Chloe, if you could set that going.
Yes, lovely. Thank you, Jonathan.
Precipitation hardenable nickel alloys are often used in subsea applications where environmentally assisted cracking is a potential risk. My name is Mike Dodge, and together with my co-investigators Mike Gittos, Kasra Satuda and David Griffiths, we undertook a review of hydrogen embrittlement of these alloys, followed by a program of environmental tensile testing and characterization to better understand this mechanism of failure. And this work was conducted under TWI CRP project 22577. The high strength and corrosion resistance of nickel chromium iron alloys, such as alloys 718, 945 and 945X, make them particularly good candidates for use in demanding environments in the upstream oil and gas industry. These materials generally perform quite well where resistance to sulfide stress cracking, chloride stress corrosion cracking and hydrogen embrittlement is required. However, environmentally assisted failures can and still do occur. It is generally accepted that for cracks to initiate, threshold conditions of stress, a susceptible microstructure and hydrogen concentration must be exceeded. Logically, adequate control of any one of these variables could prevent failure altogether, but of course this is not always practicable in the field, and a simpler approach is often to understand how these variables interact such that the risk of failure can be managed. And so our objectives of this program of work were to evaluate the influence of stress concentration and microstructure on the susceptibility of pH nickel alloys to hydrogen embrittlement. The effects of stress, hydrogen concentration and microstructure have been explored in isolation by a number of authors. However, we weren't able to find a unified source of information on the interaction between each of these three variables. In this project, the effect of microstructure was explored by heat treating alloys 718, 945 and 945X to standard and non-standard conditions. So for example, for alloys 945 and 945X, we tested the specimens in the solution heat treated condition, but also after being given a standard API 6A CRA heat treatment. For alloy 718, we did the same, but we also included an extra high solution heat treatment followed by the conventional aging step. And that high heat treatment was sufficient to dissolve any niobium bearing precipitates prior to aging. The intention of these different heat treatments was to produce alloys with various different distributions of the hardening precipitates, such as gamma prime and gamma double prime, examples of which you're seeing on the image on the right-hand side. Circular cross-section tensile specimens were machined from each of the as-received and the heat-treated coupons, such that the tensile loading direction was parallel to the rolling direction of the bars from which they were extracted. The nominal geometry of the tensile specimens are as shown here. Essentially, the gauge length was taken to be 22.5 millimeters, and the diameter of the reduced section was 6.35 millimeters. Finite element analysis was used to calculate the stress concentration factor of a sharp 1 millimeter deep notch with a notch opening angle of 20 degrees and a root radius of 0.075 millimeters. And since the notches were fully circumferential, an axisymmetric FE model representation was employed. According to the FEA simulations, the SCF at the sharp notch was found to be 20.12. And these sharp notches were prepared using wire electrode discharge machining by rotating the specimen in a motorized jig during the machining itself. Following EDM, the specimens were cleaned in ethanol. The profile of a selection of the notches were also measured using focus variation microscopy to determine the true root radius after taking into account some of the material loss that occurs during wire machining. Notch root radii of up to approximately 110 microns were measured after the machining, which corresponds to a stress concentration factor slightly less than 20. The plain-sided specimens were the same as shown here, except without the notch. The environmental test specimens from this project were subjected to cathodic protection in a 3.5% sodium chloride solution at a level of minus 1100 millivolts versus a saturated calomel electrode, which is about minus 1055 millivolts versus a silver-silver chloride electrode. After being placed in the load frame and with no load applied, the specimens were pre-charged for a period of 48 hours prior to commencing the test. Pre-charging was there to ensure that there was a residual layer of hydrogen present at the outer surface of the specimen prior to commencing testing. Both pre-charging and testing was conducted at room temperature, and pre-charging was also maintained throughout the test. We also ensured that the test vessel had a continuous supply of the electrolyte, which was recirculated throughout the vessel at all times. The crosshead displacement was selected to achieve a strain rate in the specimen of 5 × 10⁻⁶ per second. It's important to put into context that pre-charging and testing duration when dealing with austenitic materials with a face-center cubic structure. Obviously, with austenitic materials, the hydrogen solubility is relatively high. However, the diffusivity of hydrogen through the material is relatively slower than, say, a ferrous alloy, for example. So calculations were performed to estimate the proportion of hydrogen charging within the sample as a function of pre-charging duration and temperature. There are a number of variables that cannot be ascertained reliably, such as the initial concentration of hydrogen absorbed at the surface, which makes absolute prediction of the amount of hydrogen ingress quite challenging. Nevertheless, the amount of hydrogen present relative to the values initially assumed at the surface can be estimated using derivations of Fick's law. We see here these plots which are produced using literature values of diffusivity from alloy 718 from Robertson in 1977. And if we look at the distribution as a function of time, then we'll actually see that after 48 hours, which is represented by the dashed red line, we achieve approximately a depth of 50 microns of hydrogen penetration into the surface of the specimen. If you consider a typical testing duration of a further 5 days, and then we look at the green trace, which is obviously the 5 days plus the initial 2 days of pre-charging, then you can see that at the end of the test, we would expect hydrogen to permeate to approximately 100 microns deep into the sample. Now, of course, this is perhaps an overly simplistic model, as it doesn't take into consideration the fact that hydrogen likes to diffuse to areas of tensile stress, and that there's a continual supply of hydrogen to the crack tip as that crack initiates and propagates. So we're looking now at the slow strain rate tensile test results for the alloy 718 material that had not been notched. And what we're seeing is both the environmental data and the results of the specimens that were tested in air. If we look at the solution heat-treated material that had then been given an age hardening treatment and tested in air, we get very typical behavior and very nice stress strain curve with elongation values well in excess of 40%. When we look at the same specimens but tested under CP, we really start to see the effect of hydrogen. We get a large drop-off in elongation. We see a minor reduction in ultimate tensile strength. But most interestingly, we see that the yield point of both the hydrogen charged specimens and those tested in air is roughly the same. And it would appear as though the yield point itself is where we get a divergence of material properties, and that within the elastic regime, these specimens behave nominally the same. So it's only when we start to get plastic deformation that we see hydrogen take effect. And that's true regardless of the heat treatment condition. So for example, looking at the solution heat treated material, and this dark purple trace here, this is typical of a specimen that was tested in air. And this time we're getting elongation well in excess of 50%, which is what might be expected from material that hasn't been given that age hardening treatment. When that's tested under CP, we see that elongation drops off significantly to around 20%. We see a marginal reduction in UTS, and again, there's a divergence in mechanical properties roughly around the yield point. Trying to represent this another way, I've taken all of the data points for the offset proof strength and the UTS and plotted them on a graph of hardness versus those two parameters. So on the left-hand side, we have the hardness of the material versus the offset yield strength in megapascals. If we look at the results of the specimens tested in air, which are the blue points, you will see that they sit almost exactly on top of the orange points. Or in other words, we are seeing almost no difference in proof strength when we test with CP or in air. Moving to the graph on the right-hand side, however, you'll see that if I plot hardness versus the ultimate tensile strength, that there is a difference between the two results, and we see that the orange points, which are those tested with hydrogen, see a shift to the left-hand side. Or in other words, there's a consistent, small yet perceptible drop in UTS for all of the materials that were tested under CP. And all of these results here are from both the 945, 945X and alloy 718 materials. Interestingly, it's not just us that have seen this sort of effect before. The graph that you're seeing on the screen here is from the Manchester School of Materials, working with BP at the BP ICAM at Manchester. And you'll see that they've taken alloy 945, or rather 945X, and they've tested that with different heat treatment conditions, which you're seeing as the blue, the red, and the black traces. And they see a similar effect in that the elongation is reduced in every case when you test specimens which have been pre-charged with hydrogen. They also see that drop in UTS, or a slight drop in UTS. But interestingly, again, there's that divergence in material properties associated with the yield point. As part of the literature search, we began to pull out information from various different sources. So the graph that you're seeing here is elongation to failure versus the offset proof strength in air, and we've plotted various different data points. For example, we have information from Special Metals, as well as from Manchester University, Equinor, and the Colorado School of Mines, all plotted alongside TWI's data. And despite the fact that we have very different testing conditions in some of these tests, including sulfuric acid even, we're able to get quite a clear trend. And that trend is that the hydrogen-charged specimens see a greater drop-off in the elongation to failure values as the yield strength of the material increases compared to the equivalent specimens tested in air or in an inert environment. If I take the two data trends that we saw earlier, i.e. the results tested in air and the results of the hydrogen-charged specimens, and divide the environmental results by the air results, then we get what's called an environmental performance ratio. So on the y-axis here, we have that environmental performance ratio, and on the x-axis, again, we have the material yield strength of specimens following in-air testing. And we can really start to see that relationship between increasing strength and a greater drop-off in the material's performance. Moving on now towards the notched tensile specimens from TWI's work, and this time looking at the results from the alloy 945 testing, we see a very similar scenario to the specimens which were plain-sided. Rather than seeing a plot of stress-strain, you're seeing load displacement, because of course it's not possible to put a strain gauge or clip gauges over such an acutely notched specimen. Looking at the top graph here, we're seeing the solution heat-treated and age-hardened specimens which were tested in air, and those are the ones where we achieve the greatest elongation. When we test under cathodic protection, we see that the UTS drops, but again, just like the results of the unnotched specimens, there's not a significant difference in the offset proof strength of these specimens. The same is true of the specimens which were solution treated but had not been given that age hardening step, where we see a drop off in elongation, similar UTS values, but really it's again that yield point where we see the divergence in the material properties. Again, we decided to survey the literature and take various data points from notched tensile specimens that had been tested in hydrogen charging environments at slow strain rates. And despite significant differences in specimen dimensions, indeed notch acuity, for example, and also in the severity of the hydrogen charging environment, we see a very clear trend. So we've taken the notch tensile strength of the specimens tested in the environment and divided those by the test results that were from equivalent air tests, and we clearly see that as the material yield strength in air increases, there's a significant drop-off in the environmental performance ratio. One of the most interesting points, however, is the outlier that I've highlighted by the red dashed line. That is from a failure investigation on compromised material. And that's actually a precipitation hardening version of alloy 625, which is known as alloy 625 plus. Fractographically, all of the specimens that were tested in air had a similar appearance, consisting of some work hardening along the gauge length, followed by a typical cup and cone style failure. And that's exactly what we're seeing in the photograph on the top of the screen, which is from alloy 718 material that had been given an API 6A CRA heat treatment before being tested in air. If you look at the bottom of the screen, however, we see a similar specimen, but that was tested with hydrogen charging under cathodic protection. In this specimen, you see a lot less necking, but one feature that is quite important is this crosshatch pattern that we see adjacent to the fracture surface. And these are actually secondary cracks that are appearing along the gauge length. If we were to look down on the fracture surface itself of a hydrogen-charged specimen, then we would see a couple of quite distinct fracture modes. Around the outer surface of the specimen, we would get a ring of brittle fracture where we see either intergranular or transgranular facets, whereas in the center of the specimen, we would see that there's that typical ductile microvoid coalescence morphology. Between the two, we get a mixture of both, which is we would call a mixed mode failure between ductile and brittle. And all specimens that were tested under CP showed that same general appearance. We're now looking at one of the specimens that was tested under CP, and this is the alloy 945X material that was tested with a notch present. You can see exactly that brittle ring of fracture adjacent to the notch that was described on the previous slide, where we have this blocky appearance of transgranular and intergranular fracture. And as we start to move slightly further in towards the center of the specimen, we can see that there's that transition to the ductile microvoid coalescence type failure. One of the interesting observations here is that brittle ring of fracture is approximately 1 millimeter deep into the specimen, which is significantly greater than what was predicted from the hydrogen diffusion calculations. And that is because hydrogen was able to diffuse to that region of high tensile stress, and we're continually supplying hydrogen to the crack tip as the crack propagated. It's important to pay close attention to that brittle ring that we see around the outer surface of the specimen, and we're looking at an example of that here. It would be all too easy to see this blocky appearance on the fracture surface and say that it's an intergranular fracture, but actually if we begin to zoom in on it, then we see that the slip bands on the facet itself, and that's what we're seeing on the right hand image here, where we've got these diagonal lines appearing in a crosshatch pattern. And amongst those diagonal lines, we actually see that there's signs of void formation at the slip band intersections. If we look at even higher magnifications in the field emission gun, then we'll see that at the junction of those slip bands, we actually get the formation of these tiny nanovoids. So what do we think is happening? Well, there are 12 slip systems in an FCC crystal, and as we start to apply the load and as we start to go over that yield point, we begin to activate them and we get dislocation movement. At the junction of the slip bands, we then appear to be getting some interaction between hydrogen and the slip band intersections. So we're getting enhanced dislocation activity in the presence of hydrogen, and that's resulting in the formation of those nanovoids. Later on in the fracture process, we get the linking together of those nanovoids, though that doesn't necessarily have to be through a hydrogen embrittlement mode of failure. Band intersections to form nanovoids to get to embrittlement. I'm showing here a schematic where we apply the load, we get dislocation movement towards the grain boundary itself, where we might have a number of precipitates, and those precipitate can cause decohesion, resulting in an intergranular fracture surface where you often see the precipitates themselves. To summarize then, testing of the specimens under CP didn't result in significant reductions in offset proof strength. However, there was a clear relationship between increasing materials yield strength in air and reduced UTS and elongation when tested in the hydrogen charging conditions. The materials did reveal an increased notch sensitivity when tested in the presence of hydrogen, and that was particularly evident for the higher strength materials such as alloy 945X. Notch sensitivity in hydrogen manifested mainly in reduced UTS, and the increased notch UTS sensitivity was attributed to the interplay between strain localization within the notch and the propensity for hydrogen to diffuse towards highly strained and plastically deformed regions. Macroscopically, the fracture morphology of the hydrogen charged specimens consisted of a ring of brittle faceted fracture corresponding to the area where hydrogen has diffused during pre-charging and testing, and towards the center of the specimen the fracture morphology was increasingly ductile. High magnification inspection by the SEM of the embrittled portions revealed that the brittle facets were populated by slip band traces, the intersections of which were shown to be the nucleation sites for void formation. At high strains, these voids were thought to coalesce, resulting in propagation of the crack. Most importantly, though, these results show that hydrogen embrittlement, whilst macroscopically brittle, is fundamentally a high strain and dislocation activated plastic process. In this work, we looked at a very severe notch with a high stress concentration factor of 20, but there's certainly room to expand this. Some of the outstanding questions would be, how would the materials behave with less severe notches or different notch geometries altogether? And can we detect the point of crack initiation using a simple environmental test? These questions are currently being answered in a follow-on CRP project, which is 25277, the results of which should be available later this year. This project has shown that the susceptibility of precipitation hardenable nickel alloys to hydrogen embrittlement is governed by microstructure, strength, and the presence and geometry of stress razors. However, it is understood that these materials used are sensitive to the different test variables such as strain rate, pre-charging, duration, etc. It is also apparent that the tensile slow strain rate test method cannot quantify the point of crack initiation or easily distinguish between initiation and propagation. These are two fundamental aspects of environmental cracking that need to be better understood. In other words, environmental tensile testing, as conventionally carried out and without a quantified acceptance criteria, is only useful for basic screening or ranking. Appropriate guidance should be sought before applying these methods during design, fabrication and service to ensure that components are fit for service, and where possible, quantitative methods should be explored, allowing crack initiation to be captured and its significance to the environmental performance of these materials to be determined. These aspects are currently being studied in the follow-on CRP that I mentioned. A number of deliverables came out of this work, not all of which were planned. There was TWI members report 22577, which is available on our website. There's also one NACE conference paper, which has some of the results that are shown in the members report, but not all of them. We also launched a follow-on CRP, which is 25277, and the members report from that work will be available later this year. It's just going through a final review stage, having already been through feedback from the research board. We also delivered 2 lunch and learn style sessions with TWI members using teleconference facilities, and whilst the work was being undertaken and before COVID, we undertook 2 workshops in Houston with TWI members. We're also using some of the results in the hopes that we can launch a collaborative proposal later in the year. This work was funded by TWI's industrial members under the core research program. We'd like to thank Special Metals and Titanium Engineers for their in-kind contributions to the project. I'd also like to thank Gisela Rovik from Equinor for his assistance mentoring the program. Herman Amaya and Schlumberger are also thanked for supporting the follow-on project. Please feel free to contact any of us. The contact details are shown at the bottom there if you have any questions. Thank you.
As I said earlier, Michael's not with us today, but I'm sure if you send your questions through, he will respond. So this ends our enjoyable session. I'd like to thank our presenters, Mohammad, Tianmiao, and Michael. So I'd like to end the session and hand you over to Chloe, who will make a few closing remarks, I hope. Thank you.
I will indeed, lovely. Thank you very much, Jonathan. So I just wanted to apologise for a couple of technical issues in the video. If anyone does have any questions they'd like to ask Mike, then please do send them across, or you can send them to our team, which is inquiries@nsirc.co.uk, and we'll pass on your questions to him there. So we hope you enjoyed the first day of our NSIRC Research and Innovation Conference for 2021. We've seen a good range of topics, including composites and polymers, additive manufacturing, Industry 4.0, structural integrity, and finally, joining technologies. This is the first time we've included our core research programme in our agenda, and we hope it's been well received by you all and that you've learned a little bit more about some of the projects being undertaken at TWI through CRP. So thank you to all of our presenters today. We've had some of our best presentations yet, and I look forward to hearing the rest tomorrow. A big thanks again to our sponsors of this year's conference. You can find out more information about each company or university via our website. And lastly, I would like to thank our fantastic chairs and judges from each of our technical sessions today. You've done a great job at managing the rooms, and we can't thank you enough for the time you've committed to the conference today and also leading up to it. So thank you. We hope to see you all again tomorrow morning at 9:30 UK time, where our keynote speaker will be Mark Thompson, who is the Executive Chair at the Science and Technology Facilities Council, talking about why technology matters in today's world. So thank you again for joining the first day of our NSIRC Research and Innovation Conference. Have a good evening, and I will bid you farewell. So thank you.